At the edge of the solar system, far beyond Pluto and the icy worlds of the Kuiper Belt, there may be something vast and invisible, a frozen sphere of ancient objects spread out like a halo around our sun. We've never photographed it, and yet, for decades, scientists have been almost certain it's there. They call it the Oort Cloud. The Oort Cloud sits at the boundary of what we know and what we think we know. Could something out there be disturbing it? An unseen star, a passing rogue planet, or something stranger? Is it possible the Oort Cloud marks the physical edge of our universe, or even the edge of our simulation? When we first suspected something was out there, the birth of the Oort hypothesis. In 1950, a Dutch astronomer named Jan Oort proposed something that would change how we think about the outer limits of our solar system. He suggested that far beyond the planets, including Pluto, there might be a vast cloud of icy objects. The clues, he believed, were already in front of us, hidden in the strange orbits of comets. For centuries, comets had puzzled astronomers. They would appear in the sky suddenly, often trailing long glowing tails, and then vanish just as quickly. Some returned again after many years, while others never came back. Astronomers had been tracking these objects for a long time, carefully noting their paths across the sky. And by the mid-20th century, enough data had been collected to see patterns emerge. The key clue was the shape and speed of the orbits of long-period comets. These are comets that take hundreds of thousands, sometimes even millions of years to circle the Sun. When astronomers looked closely at these comets, they found that many had extremely distant aphelia, or farthest points from the Sun. The starting points of their journeys seemed to lie far beyond the known solar system. More curious still, the directions they came from appeared random. If the icy bodies beyond Neptune were arranged in a flat disk, we would expect to see comets entering from roughly the same plane. But that's not what we observe. Instead, long-period comets appear from all directions in the sky. Some come from above the solar system's plane, others from below, and some arrive almost sideways. That kind of pattern only makes sense if they are coming from a large three-dimensional structure, something like a sphere. Oort began analyzing the mathematics behind these cometary orbits. If the comets had been orbiting the Sun for billions of years, making passes close to it and then swinging far away again, their orbits should have been more tightly wound. Gravity, collisions, and other forces over time would have reshaped their paths. But these comets didn't show signs of long-term wear. Their orbits looked fresh, almost like they had just begun their journey into the inner solar system. This was a big clue. Oort realized that many long-period comets had probably only made one trip into the solar system. That meant they were coming in from the outside for the very first time. So where were they coming from? Oort theorized that these comets must be stored in a kind of reservoir far away from the Sun, a place where they could remain frozen and untouched for billions of years. Occasionally, one of these icy bodies might get disturbed and be nudged into a new path. Once disturbed, it would fall toward the Sun, becoming a comet with a long, arcing orbit. He estimated that this cloud must begin tens of thousands of times farther from the Sun than Earth is. In fact, he proposed that it could stretch out nearly a quarter of the way to the nearest star. This was an enormous distance, far beyond where any planet or asteroid had been seen. Oort wasn't suggesting a neat, organized ring like Saturn's or the asteroid belt. He pictured something much vaster and more diffuse, a giant sphere of icy fragments, all slowly orbiting the Sun from afar. Each object in the cloud may be separated from its neighbors by millions of kilometers. This idea helped answer a number of long-standing questions. For one, it explained why comets could still be so bright and full of ice, even after billions of years. If they had spent their lives in the inner solar system, they would have long since melted and faded. But if they spent most of their time in a dark, frozen region on the solar system's edge, their icy cores could remain preserved. It also helped explain why comet paths didn't follow a single plane like the planets. If they were coming from a spherical cloud, it made sense that they would approach from all directions. Oort wasn't the first to wonder about the origin of comets. Earlier, in the 1930s, an Estonian astronomer named Ernst Öpik had also suggested that comets might come from a distant unseen cloud. But it was Oort who took that early idea and expanded it, putting numbers to the distances and studying the actual orbital data to support the theory. Because of this, the concept became closely tied to his name. Today it's known as the Oort Cloud, though some also call it the Oort Cloud. At the time, this was a bold proposal. Even now, 3/4 of a century later, we still haven't imaged a single object from it. The cloud is too far away, and its objects are too small and dim to be picked up by telescopes. But the patterns in the orbits of long-period comets remain consistent with Oort's idea. Each time a new one appears and astronomers trace its origin, the story fits. It seems to have come from somewhere in that distant shell of icy debris. What made Oort's hypothesis so powerful was not just that it offered a neat explanation for comet behavior, it opened up a whole new realm of the solar system. Until then, most astronomers had pictured the solar system as ending with Pluto. Beyond that was assumed to be mostly empty space. But Oort suggested that the Sun's gravitational influence stretched far beyond what we could see, and that it was still shaping the movements of icy objects on the very edge of interstellar space. This changed the way scientists thought about the solar system's size and structure. It hinted at a vast and hidden zone of cold, ancient material. Perhaps these were leftovers from the solar system's formation, bits of ice and rock that never made it into a planet. Or maybe they were even older, fragments from before the Sun itself was born, captured during the early days of our solar neighborhood. The idea also raised many new questions. How stable is this cloud? Could it be disturbed easily by stars or galactic tides? And what would happen if a large number of its objects were suddenly nudged toward the inner solar system? Could this explain periods in Earth's history when many comets seem to have arrived at once? Jan Oort may never have seen the cloud that bears his name, but his careful reading of the signs left by comets led to one of the most enduring ideas in astronomy: the farthest frontier, differentiating the outer Oort cloud from the inner Hills cloud. Over the years, scientists have come to believe that the Oort cloud has two main parts, an outer region and an inner one. Most people only hear about the outer part, the one that sends long-period comets flying in from deep space. But hidden closer in, there may be another layer, a dense and quieter region called the Hills cloud. The idea of two separate regions wasn't part of Jan Oort's original hypothesis in 1950. But as astronomers began to gather more data and study the behavior of these icy objects, patterns started to emerge. Some comets had orbits that didn't stretch as far as others. They didn't seem to come from the extreme edge of the solar system, but from somewhere a little closer in. The outer part of the Oort cloud is believed to begin at around 20,000 to 50,000 astronomical units from the Sun, and may extend out to 100,000 or even 200,000 astronomical units. At this distance, the Sun's pull is incredibly weak. Objects out there are barely bound by its gravity. The tiniest push from a passing star, a molecular cloud, or the gravitational tides of the Milky Way can knock these bodies off course. That's why the outer cloud is thought to be the source of most long-period comets. But deeper inside, closer to the Sun, yet still far beyond the known planets, lies the inner Oort cloud. This part is sometimes called the Hills cloud, named after astronomer Jack G. Hills, who proposed its existence in the 1980s. Hills suggested that the solar system needed a reservoir of icy bodies that was more stable than the outer cloud. While the outer region gets disturbed easily and loses objects to interstellar space, the inner region would act more like a storage area. Its bodies would stay in place for longer periods and slowly refill the outer cloud as it thinned out. The Hills cloud is believed to start somewhere around 2,000 or 3,000 astronomical units from the Sun and stretch out to 20,000 or 30,000 units. It's much closer in than the outer cloud, but still far beyond the orbit of Neptune. Objects in the Hills cloud are held more tightly by the sun's gravity. Because of that, they are not as easily disturbed. They stay put, waiting in silence for some rare event, maybe a collision or the passing influence of a giant planet, to send them drifting inward. If the outer Oort cloud were the only source of these icy visitors, we would expect it to run out more quickly. The outer cloud gets drained by gravitational nudges that fling comets away forever, yet we still see new long-period comets appear with regularity. This suggests that there must be a hidden supply, a more stable reservoir, that slowly sends fresh comets outward, keeping the outer cloud full. That's where the Hills cloud fits in. It may be doing the quiet work of maintaining the outer cloud over long timescales, and it could be much more massive than the outer shell. Some researchers believe that as much as 90% of all the mass in the entire Oort cloud is stored in the Hills cloud. That means most of the icy bodies orbiting beyond Neptune are not sitting at the extreme edge, but are gathered in this inner zone, hidden and untouched. The reason we don't see more comets from the Hills cloud is simple. They don't get disturbed as often. It's only when something rare happens, perhaps a shifting alignment of the planets or a rogue star wandering close, that one of these objects is nudged just enough to fall inward. When that happens, it may pass through the outer Oort cloud, pick up more energy, and arrive in the inner solar system as a new comet. The shape of the Hills cloud might not be the same as the outer Oort cloud. While the outer part is thought to form a near-perfect sphere, the inner cloud could be more flattened, maybe more like a thick disk or an extended bubble that bulges around the edges. Some models suggest it may even be slightly tilted compared to the plane of the solar system. But without direct observations, all of this remains guesswork based on how comets behave and how the solar system likely formed. Computer simulations have helped researchers explore how the two clouds may have developed. In the early solar system, as the giant planets grew and moved through the disk of gas and dust, they scattered icy objects outward. Some of these objects were ejected into interstellar space. Others found their way into long orbits, becoming part of the outer Oort cloud. But many were placed in orbits that were not far enough to escape completely, yet not close enough to remain among the planets. These became trapped in a kind of halfway zone. If the Hills cloud is real, it might also contain some of the most pristine objects in the solar system. They may carry the chemical fingerprints of the early solar nebula, the cloud of gas and dust from which everything formed. Studying them, if we ever find a way to reach them, could reveal secrets about how the solar system began. Some researchers have suggested that large bodies, even planets, could be orbiting in this zone. These ideas remain speculative, but they reflect just how little we know about the deep outer solar system. It is a realm of silence, of frozen shadows and invisible paths, where the sun is no brighter than a distant star. A cloud of chaos. Could the Oort region be a graveyard of solar system debris? The early solar system was not a calm place. It was wild and violent. The sun had just formed from a swirling cloud of gas and dust, and all around it, clumps of matter were sticking together, colliding and growing. Some of these clumps grew large enough to become planets. Others were swept up by those planets or thrown into the sun. But not everything found a home. Some objects were pushed away. These misfits, too small to grow into worlds, too far to be pulled back, ended up in the outer reaches. The idea that the Oort cloud is a leftover region goes back to the way comets behave. When astronomers study the ingredients in comet tails, water ice, carbon compounds, frozen gases like methane and ammonia, they see a kind of time capsule. If these comets were stored in a faraway cloud, protected from solar radiation and cosmic events, it would explain how they remained so well preserved. But it also means that the Oort cloud isn't some smooth or elegant structure. It's more like a vast junkyard, a place filled with objects that never found a purpose. Some may be oddly shaped, cracked, or partly broken. Others might be combinations of rock and ice, frozen together by chance. No two objects are expected to be exactly alike. This cloud of chaos, far from the sun, represents the cast-offs of creation. Some scientists think that the story of how these objects got there is tied to the movements of the giant planets, especially Jupiter and Saturn. As these massive worlds grew, their gravity began to influence nearby material. They acted like cosmic slingshots, flinging small objects outward with incredible force. Many of these pieces didn't escape the Sun's gravity completely, but were placed into long, looping orbits. Over time, some of those orbits became more stable, settling into the spherical pattern we now associate with the Oort Cloud. But it wasn't just the planets that shaped this icy shell. The galaxy itself played a role. The Sun, as it orbits through the Milky Way, passes near other stars and moves through giant clouds of gas. Each of these encounters can nudge the orbits of faraway objects, shifting them gently or knocking them into new paths. Over billions of years, these small changes added up. The orbits of the icy bodies in the outer regions became more random, spreading them out into the cloud we suspect surrounds us now. There's also the possibility that not everything in the Oort Cloud came from here. Some researchers have wondered if the Sun, in its early days, may have stolen material from other stars. If the Sun formed in a dense cluster, a nursery filled with other young stars, then their gravity fields would have been overlapping and chaotic. Some icy objects from neighboring systems may have been captured and drawn into our own cloud. That would mean the Oort Cloud isn't just our solar system's graveyard. It could also be a mix of debris from multiple stars. What's important to understand is that the Oort Cloud likely holds more material than all the known comets put together. The comets we see are just the ones that got knocked out of place and sent inward. For everyone that reaches the inner solar system, there could be thousands more staying quiet in the cold. The Oort Cloud may also help explain why some strange comets appear suddenly and seem to come from nowhere. In some cases, these objects have never been seen before and don't follow the same orbital paths as others. Inside this icy cloud, conditions are silent and dark. There is no light, no heat, and no activity. The Sun appears only as a faint star. Space is almost empty, with each object separated by vast distances. Collisions are rare, movement is slow, time passes differently here. It is the most isolated region of the solar system. Some scientists refer to the Oort Cloud as a cosmic archive. It may contain records of how the solar system formed, what materials were present, and how they changed over time. But others see it in a more haunting way, as a kind of cemetery in space. Not a place of burial, but of abandonment. It's where all the bits that didn't quite fit have gone to drift, perhaps forever. If the solar system ends at the Oort Cloud, where does interstellar space begin? For a long time, people thought the solar system ended where the last planet orbited. Once you got past Neptune, that was it. But as our knowledge grew, we realized that gravity stretches much farther. So where then does the solar system really end? That depends on how you define it. One way to think about it is by gravity. As long as the Sun's gravity can still hold on to something, like a comet in the Oort Cloud, it's part of the solar system. And by that rule, the solar system could be up to 2 light-years across. That's about halfway to the next nearest star, Proxima Centauri. It's an enormous distance, far beyond anything we can easily picture. But gravity isn't the only way to define a boundary. There's also something called the heliosphere. This is the bubble of space created by the solar wind. The constant stream of charged particles the Sun sends out in all directions. The solar wind pushes against the gas and dust floating between the stars. At some point, the pressure from the rest of the galaxy pushes back hard enough to stop the solar wind. That place is called the heliopause, and it's often used as a marker for the edge of the solar system. The heliopause isn't in a fixed location. It changes based on the Sun's activity and the pressure of the interstellar medium, but generally, it's thought to be about 120 times farther from the Sun than Earth is. That's still far inside the Oort Cloud. In fact, it doesn't even reach the inner edge of it. The heliopause is only about 120 AU, so even beyond where the solar wind stops, the Sun's gravity still rules. In 2012, something important happened. Voyager 1, a spacecraft launched in 1977, crossed the heliopause. For the first time, a human-made object had left the bubble of the solar wind and entered interstellar space. But even then, it hadn't left the solar system entirely, not if you go by gravity. Voyager 1 is still under the Sun's gravitational pull. It's still years, maybe centuries, away from passing the edge of the Oort Cloud. And yet, it had already entered a new environment. One where the particles and magnetic fields no longer come from the Sun, but from the wider galaxy. This shows just how fuzzy the boundary really is. You can define the edge of the solar system in several ways. If you go by planetary orbits, it ends with Neptune or Pluto. If you go by the solar wind, it ends at the heliopause. If you go by gravity, it might not truly end until 2 light-years out. Each boundary tells a different story. There's also the Sun's influence in terms of radiation and light. As the Sun's light spreads out into space, it gets weaker. Eventually, it's drowned out by the light from other stars. That's another kind of boundary. The point where the Sun is no longer the brightest light in the sky. But again, that doesn't give us a clean edge. It's just another gradual shift. Scientists often use the word interstellar to mean space between stars, not just outside a planet's orbit. But even then, the idea of a boundary becomes tricky. The space between stars isn't empty. It's filled with gas, dust, radiation, and magnetic fields. It's a busy place, even though it seems like a void. As our solar system moves through the galaxy, it plows through this interstellar medium, creating a kind of bow wave, like a boat moving through water. The shape of this interaction also changes where the heliosphere ends and where interstellar space begins. The Oort Cloud floats in this in-between zone. It's still under the Sun's control, but it's close to the edge. It's like a fence line that stretches into a fog. You can't quite see where the property ends, but you know it does eventually. Objects in the outer part of the Oort Cloud might be so loosely held that the passing of another star could knock them free. Some might already be drifting away without us even knowing. From time to time, other stars pass near our solar system, at least near in cosmic terms. They don't come close to the planets, but they might pass within a light-year or so. When they do, their gravity tugs at the outer edge of the Oort Cloud. These close encounters remind us that the Sun doesn't live in isolation. It travels through the galaxy like a ship on a vast ocean, carrying its bubble of space along with it. That bubble is stretched and shaped by the winds and currents around it. And the outer edge is always changing. Even as we send probes like Voyager into these distant regions, we're still only beginning to understand them. The data we get is limited and slow. The spacecraft take years to move even a tiny step further, and yet every new reading tells us more about how the Sun interacts with the galaxy around it. For now, the Oort Cloud marks a kind of soft edge. It's where our solar system starts to blend into the wider universe. Beyond it, the stars take over. Their gravity becomes more important. It's not that we suddenly cross into a new space. It's more like we fade into it. The Oort Cloud is our outer skin, thin but still part of us. The galactic tug-of-war, how passing stars sculpt the Oort Cloud's shape. Our solar system moves around the center of the Milky Way, completing a wide orbit that takes hundreds of millions of years. Along the way, it passes through different regions of space. Sometimes those regions are more crowded, and sometimes another star wanders close enough to make a difference. To be clear, close in space doesn't mean what it means on Earth. A star might pass within a light-year and still be considered very near. That's still about 63,000 times the distance from Earth to the Sun. But even from that far away, a star's gravity can tug at the outer edge of the Oort Cloud. These small distant pulls happen over long periods of time, but when added up over millions of years, they can change the entire shape of the cloud. They nudge comets into new paths. They may even pull some objects out completely, stealing them into the galaxy. Others might be pushed inward, toward the planets, becoming the long-period comets we sometimes see glowing in our skies. Over time, scientists have tried to match known comet paths with records of nearby stars. A few candidates have emerged. One of the most talked about is a small faint star named Schultz's star. About 70,000 years ago, it's believed to have passed within less than a light-year of the Sun, possibly right through the outer edge of the Oort Cloud. That's close enough to disturb the fragile orbits of many icy bodies. It may have caused a few to start drifting toward the inner solar system. Some of those may not have arrived yet. The journey in from the edge can take millions of years. These flybys aren't rare on a galactic scale. Every few 100,000 years, another star may pass close enough to reach the Oort Cloud. Sometimes it's a big star with strong gravity. Other times it's a smaller red dwarf, or even a rogue planet without a star of its own. Each encounter adds a little bit of change. The shape of the cloud bends and stretches. Sometimes it thickens in one direction. Other times it thins out. The result is a shell that isn't perfectly even. It's more like a wobbling sphere, pushed and pulled by invisible hands. There's also another force at work, the tide of the galaxy itself. Just as the moon causes tides on Earth, the Milky Way has its own kind of pull. As the solar system moves through the galaxy, the overall gravity from the stars, gas, and dark matter all around us can tug gently on the Oort Cloud. This galactic tide acts slowly, but over long periods, it has real effects. It can stretch the cloud into a wider shape. It can help shake loose objects at the edge. In some ways, it's always trying to strip the cloud away from the sun. This combination of passing stars and the galactic tide helps explain why the Oort Cloud is spherical. That makes sense if it's constantly being pulled at from all sides. Over billions of years, this kind of gravitational stirring would have erased any flat shape and puffed the cloud into a round shell. Some scientists think that these constant nudges may also be one reason we still have an Oort Cloud at all. If left alone, it's possible that many of the icy bodies in the cloud would have stayed where they were forever. But with passing stars and galactic tides giving them the occasional push, some of them are knocked off balance. They begin the long fall toward the inner solar system, where we may eventually spot them as new comets. In this way, the galaxy helps deliver these ancient visitors. But the same forces that send comets inward can also take parts of the Oort Cloud away for good. Over the course of the solar system's life, it may have already lost much of its original cloud this way. Some of those lost objects might still be drifting through the galaxy today, no longer tied to any star. They could be anywhere, hidden in the dark between the stars. Other solar systems might have lost chunks of their own clouds too, leading to a kind of mixing. Perhaps our Oort Cloud even holds a few strangers, objects that once belonged to another star, captured during a close flyby long ago. Nemesis, the Sun's hypothetical companion and the disruption of the cloud. The idea of Nemesis came from a pattern, one that seemed to show up in Earth's history, buried in stone. Around the early 1980s, a pair of physicists, Richard Muller and his colleagues, noticed something strange while looking at extinction events in the fossil record. Mass extinctions, those sudden disappearances of life, seemed to happen not randomly, but in regular intervals. Roughly every 26 million years, something catastrophic seemed to strike Earth. Some scientists began to wonder if this cycle could be caused by something outside our planet, something far beyond it. Maybe they were caused by huge icy missiles from the edges of the solar system or comets. And maybe something was stirring up those comets on a regular schedule. The theory that followed was bold. What if the Sun had a partner, a companion star, orbiting far beyond the planets? Every 26 million years, it might swing in close enough to disturb the Oort Cloud, sending a storm of comets raining toward the inner solar system. They imagined this companion star as small, dark, and hard to find. It wouldn't shine like our Sun. It might be a red dwarf, or even a brown dwarf, a failed star that never truly ignited. If it were out there, it would be hard to see. It might take years to find, but if it existed, it could explain not just extinction cycles, but sudden surges in comet activity. A companion star like that, they believed, would act like a galactic troublemaker, stirring up the outer cloud every time it passed near. The name Nemesis came naturally. In Greek mythology, Nemesis was the goddess of vengeance, an unseen force that arrived to punish and restore balance. In this version of the story, the sun's partner was not friendly. It was distant, dark, and capable of bringing destruction. The idea caught the imagination of scientists and the public alike. If true, it would mean our solar system wasn't a solo act. It would mean the Oort Cloud wasn't just shaped by passing stars and galactic tides, but by a hidden player orbiting alongside us. And for years, astronomers searched for this invisible twin, but Nemesis remained elusive. No telescope could find it. Infrared sky surveys, which could spot cold stars and brown dwarfs, turned up nothing in the right range. If Nemesis existed, it would have to be either incredibly dim or incredibly far away, possibly both. The more searches came up empty, the more doubt began to creep in. Still, the concept of a solar companion fits into a broader picture of how star systems work. Many stars in the galaxy are not alone. In fact, more than half of all Sun-like stars are part of binary or multiple star systems. Twins and trios are common. In that light, the idea of the Sun having a companion didn't seem so strange. Maybe we started with two, and one was thrown out early on. Or maybe Nemesis was never close. Maybe it always orbited from afar. A companion star on a long looping orbit would move slowly through the darkness, taking tens of millions of years to complete a single circuit. But when it approached the dense parts of the Oort Cloud, even a small gravitational pull could be enough to send thousands of icy bodies tumbling inward. Most would miss Earth. Some would flash across the sky. But a few might hit, and if big enough, change life on our planet forever. Models of this kind of interaction show a kind of cosmic sweeping motion. Nemesis would pass through the outer edge of the cloud, jostling it just enough to disturb the balance. It wouldn't need to come very close. The Oort Cloud is so loosely held that even far-off nudges can matter, and because the companion's orbit would be so long, its visits would be spaced out, possibly lining up with extinction patterns seen in Earth's deep history. There are also other versions of the idea. Some suggest the Sun's companion wouldn't need to be a star at all. It could be a massive planet, something larger than Jupiter, hidden even farther out than the known planets. Others link the idea to Planet 9, a different hypothesis about a giant unseen planet that may be shaping the orbits of far-off objects in the Kuiper Belt. While Planet 9 is thought to lie much closer than Nemesis would, the two ideas have similarities. Some scientists remain skeptical. They point out that the extinction cycle, if it exists at all, could be caused by many things. Climate change, volcanic activity, or even random chance might explain the fossil record just as well. And without real evidence of a companion, the Nemesis theory stays in the realm of speculation. Still, if Nemesis, or something like it, does exist, it would be the most distant member of our solar family. Its orbit would stretch far beyond the planets, curving deep into the black, past the zone of comets and cosmic dust. Its return would be rare, its effects slow but powerful. Even without proof, the Nemesis theory helps remind us that the edge of the solar system isn't sealed off. It's part of a bigger neighborhood. Things can come and go. Gravitational waves, drifting stars, and perhaps even long-lost companions can all shape the cloud's contents. The outer solar system is mostly uncharted. We've sent probes to the planets. We've mapped asteroids, but the Oort Cloud remains a ghostly mystery, and anything hiding inside it, whether a brown dwarf, a giant planet, or just millions of icy fragments, still remains beyond our sight. The Shiva hypothesis. Are mass extinctions linked to Oort Cloud disturbances? The Shiva hypothesis, named after the Hindu god of destruction and renewal, suggests that every so often something disturbs the Oort Cloud and sends a wave of comets crashing into the inner solar system. With enough speed and size, a single impact could set off a chain reaction, dust blocking the sun, temperatures dropping, food chains collapsing. Life on Earth would change overnight. Supporters of the Shiva hypothesis began pointing to one extinction event in particular, the one that ended the age of the dinosaurs. About 66 million years ago, something massive hit the Earth near what is now the Yucatan Peninsula in Mexico. The crater it left behind, called Chicxulub, is more than 100 miles wide. All around the world, a thin layer of rock marks the moment it happened. That layer is rich in iridium, a rare metal that's common in asteroids and comets, but not on Earth's surface. It was the smoking gun. Something from space had hit the planet, and it was likely the cause of the mass extinction that followed. The big question was, why then? And could this impact have been just one in a larger pattern? The Shiva hypothesis takes this idea a step further. It says the Chicxulub event wasn't just a random strike. It might have been part of a cycle, one that happens every few tens of millions of years. The cycle could be caused by different things. Maybe the solar system moves through dense parts of the galaxy. Or maybe the gravity of the Milky Way itself creates a repeating force. But whatever the cause, the effect would be the same. Comets would be knocked loose from the distant cloud, and some would head toward Earth. When researchers ran computer simulations of how this could work, they found that even small changes, like the solar system's tilt changing, could shake the Oort cloud up. In those moments, the cloud might release thousands of comets into long, looping paths that bring them closer to the Sun. Most of these icy travelers would be seen only through telescopes. But once in a while, one might cross paths with our planet. Not all scientists agree with the Shiva hypothesis. Some believe the timing of extinction events isn't as regular as it seems. They say the fossil record is messy and hard to date with perfect accuracy. Others point to volcanoes or rising carbon dioxide levels as the true causes of most extinctions. Still, the idea of a space-based trigger won't go away. Some scientists are looking closely at whether comet showers might happen in bursts, not just single events. If a large group of comets is shaken loose all at once, the chances of one hitting Earth go up. This is especially true if they all follow similar paths. A single pass through a dense part of the galaxy could launch a wave of these comets inward. The Earth has been hit many times before. Some impacts have left behind massive craters. Others likely hit the ocean and left no trace. Over millions of years, erosion and plate tectonics have erased many signs. But we know from the Moon, where there is no weather to wash things away, that big impacts have happened often in the solar system's past. One part of the Shiva hypothesis that continues to raise interest is the idea of correlation, not just with craters, but with periods of rapid evolution. After many mass extinctions, life seems to rebound in new and surprising ways. New species appear, ecosystems rebuild. It's almost as if destruction clears the way for creation. Just like the god Shiva in mythology, the force behind the extinctions may also be part of a longer story, a cycle of death and renewal. In the last few decades, astronomers have found more long-period comets than ever before. With better sky surveys and more powerful telescopes, we're starting to build a better picture of where these comets come from and how often they arrive. Researchers are also digging deeper into Earth's past, looking for signs of other impacts hidden in the layers of rock. There's also interest in looking beyond comets alone. Some theories suggest the same events that shake up the Oort cloud might also cause changes in the Sun's output, or even trigger volcanic activity on Earth. In this broader version of the hypothesis, mass extinctions could have multiple causes working together. Comets, climate change, and geological activity all happening in the same window of time. If the Shiva hypothesis is right, then the next comet shower might be waiting in the darkness, just beyond the edge of sight. Why the Shiva hypothesis faces fierce criticism and why it still won't die. Many scientists have deep doubts about the Shiva hypothesis. Rocks erode, fossils break, entire layers can go missing. Trying to find a steady pattern in this jumble is extremely hard. Even with today's technology, we still struggle to pinpoint the exact timing of many extinction events. Some researchers argue that when people claim to see a pattern, like extinctions happening every 26 or 30 million years, they may be seeing what they want to see, not what's really there. It's easy, they say, to draw lines between events when you already believe a pattern exists. The Shiva hypothesis also depends on something shaking the Oort cloud every so often, sending comets into the inner solar system. But what does that shaking? Nemesis has never been found. And while the Sun does move up and down through the plane of the Milky Way, the timing doesn't match the proposed extinction cycle exactly. Without a clear trigger, the whole idea becomes harder to accept. Critics also say there just aren't enough known comet impacts to support the theory. We know the Earth has been hit in the past, but there's no clear sign of multiple global-scale impacts happening in a tight cluster every few million years. And while comets do still fall into the inner solar system, their numbers are small. Even when we look back using crater counts and ancient rock layers, the evidence for repeated comet showers just isn't strong enough for many experts. Another issue is that some mass extinctions don't look like they were caused by impacts at all. Take the Great Dying about 252 million years ago. It was the worst extinction in Earth's history, wiping out around 90% of marine species. But there's no confirmed impact crater tied to that event. Instead, many scientists believe it was caused by massive volcanic eruptions in what is now Siberia. These eruptions poured out huge amounts of lava and gas, warming the planet and filling the oceans with toxins. In cases like this, there's little reason to bring comets into the picture. So why does the Shiva hypothesis keep coming back? Part of it may be psychological. Humans are drawn to big, sweeping ideas. The thought that every few million years, something from deep space comes crashing into our world is both terrifying and fascinating. It gives a feeling that we are part of a larger cosmic story, that the universe is not just out there, but involved in our history. For some people, it offers a simple explanation for complex events. Instead of looking at dozens of different reasons for mass extinctions, the Shiva hypothesis wraps it all into one clean theory. It's dramatic, easy to picture, and fits well into headlines and documentaries. There's also the fact that while the hypothesis has many problems, it hasn't been entirely ruled out. Some scientists keep studying it because the basic idea that the Oort cloud can be disturbed and that disturbed comets can hit Earth is true. It's the timing and impact of those events that remain uncertain. If just one of the past extinction events was triggered by a comet, then the Oort cloud has played a role in shaping life on Earth. That's enough reason to keep looking. Others continue to explore it because we are still learning so much about the outer solar system. Only recently have we started to understand the size and shape of the Oort cloud, or to find objects far beyond Pluto that might hint at hidden masses. As our knowledge grows, so does our ability to test these old theories. What seemed impossible to prove a few decades ago might soon be testable with better data. Some researchers believe that once we start mapping long-period comets in more detail, we may see if they arrive in clusters, as the hypothesis predicts. If that happens, the idea could gain new support. There's also a historical lesson here. In science, ideas that seem wild or fringe can sometimes turn out to be right. When the theory of continental drift was first proposed, it was laughed at by many geologists. The idea that continents could move sounded absurd. It took decades of new data, especially from the ocean floor, before people realized it was true. Supporters of the Shiva hypothesis believe something similar might happen here. They think that as we learn more about the outer solar system, we might finally uncover the missing links. In recent years, the debate has become more detailed. Researchers are trying to figure out how comet showers would actually look. Would they show up as a sudden burst of impacts, or a slow trickle over thousands of years? Would they leave a chemical signature in rocks like a spike in rare elements? Can we match these patterns to extinction events with enough accuracy to say something meaningful? There's also growing interest in building better models of the Oort cloud itself. If we can understand how it reacts to outside forces, we can make better guesses about what kind of disturbances could send comets our way. New sky surveys and space telescopes will also help by spotting more long-period comets. The more we know about their paths and timing, the more we can test whether they really come in waves. For now, the Shiva hypothesis remains in a strange place. It's not widely accepted, but it's not fully dismissed either. Some keep pushing it forward, searching for patterns, refining models, and hoping that someday the full story will come into focus. Others keep a more cautious stance, asking tough questions and looking for better answers. How close have we come to the Oort Cloud? The Voyager spacecraft were launched in the late 1970s, first Voyager 2 in August of 1977, then Voyager 1 a few weeks later. Their mission was to explore the outer planets, Jupiter, Saturn, Uranus, and Neptune. No one knew how long they would last, but their designers built them to survive. Now, almost 50 years later, both Voyagers are still out there, still sending signals. They have become more than scientific tools. They are symbols of curiosity, of endurance, of how far we've come. Voyager 1 is now the most distant object ever created by humans. It passed the orbit of Pluto in 1990. It entered interstellar space in 2012, according to NASA. Interstellar space, in this context, means it crossed the heliopause. 1 astronomical unit, or AU, is the distance from the Earth to the Sun, about 93 million miles, or 150 million kilometers. Voyager 1 is currently just past 160 AU. That's impressive, but it's only about 3 to 8% of the way to the Oort Cloud's closest edge. In other words, even after almost 50 years, Voyager 1 hasn't yet touched the cloud's doorstep. And that's just the inner edge. The outer Oort Cloud might stretch as far as 100,000 AU. To reach even the midpoint of that range, it would take Voyager 1/10 of thousands of years, assuming it keeps moving and isn't pulled off course by a rogue object. In practical terms, the Oort Cloud is unreachable with current technology. Voyager 2 is not far behind its sibling. It took a slightly different path, allowing it to fly past Uranus and Neptune. Its instruments are still working, though some have been shut down to conserve power. Like Voyager 1, it is heading outward, into the unknown, at a steady pace of around 15 kilometers per second. It also has not reached the Oort Cloud and is unlikely to do so before its power systems fail. Then there's New Horizons, the probe that famously flew past Pluto in 2015. It was launched in 2006 and traveled faster than any spacecraft before it, reaching the dwarf planet in just under a decade. After its Pluto encounter, it continued into the Kuiper Belt and made a close flyby of a distant object known as Arakoth. That object, a frozen remnant from the early solar system, sits at about 44 AU from the Sun, well beyond Neptune, but still nowhere near the Oort Cloud. New Horizons is still active, still sending back data. It's expected to operate until around 2040, depending on its power levels. By that time, it might reach a few hundred AU from the Sun, but again, that's just a fraction of the distance to the Oort Cloud's edge. These spacecraft, even the fastest ones we've ever launched, are not built to cross the Oort Cloud. They simply drift in its direction. The truth is humbling. Every picture of the Oort Cloud you've seen is an illustration. Every map that shows it is a model. It remains for now a theoretical place. To get a better sense of just how distant it is, consider this. Light from the Sun takes about 8 minutes to reach Earth. It takes about 5 hours to reach Pluto. To get to the inner edge of the Oort Cloud, light would need almost a full month. The outer edge? Over a year. Reaching it would require spacecraft far more advanced than anything we've built. Some scientists have talked about sending probes using new types of propulsion. There are concepts for missions that could reach the Oort Cloud in a few hundred years, instead of tens of thousands. But so far, these ideas remain on paper. Any mission designed to reach the Oort Cloud would take so long that the scientists who built it would never live to see the results. It would be a project measured in generations. That kind of thinking is hard to fund, hard to plan, and hard to justify in a world where most missions are expected to deliver results within a few decades. Still, there are signs of hope. With each passing year, our technology improves. Missions like the James Webb Space Telescope and future large survey telescopes may help us detect more distant objects, some of which could be related to the Oort Cloud. A better understanding of these objects could help us design missions that are more targeted, more efficient, and better prepared for the long trip outward. There's also growing interest in what lies beyond the solar system. As we learn more about exoplanets and other stars, we begin to see our sun not just as a light in the sky, but as one of many. This broader view makes the Oort Cloud feel like a bridge, a region that connects the sun's domain to the vast galaxy beyond. If we ever want to truly explore interstellar space, we will first have to cross the Oort Cloud. Can we ever see the Oort Cloud? Astronomy often moves forward not by taking steps, but by taking leaps. There was a time when the idea of seeing planets around other stars sounded like science fiction. Now we know thousands of them. There was a time when black holes were only theories. Now, we've taken a picture of one. So the question hangs over the Oort Cloud like a challenge. Can we ever see it? Can we stop imagining and start observing? The truth is, we don't need to fly all the way there to confirm it exists. If we can't send a probe, at least not yet, then we have to use the tools we already have. That means light, gravity, and the clever use of shadows. It means learning to look at the sky in different ways, with different eyes. One of the most hopeful paths is infrared astronomy. Even though the objects in the Oort Cloud are cold, they aren't at absolute zero. They still give off a small amount of heat. Not enough to be seen by human eyes, or even most visible light telescopes, but possibly enough to show up in the infrared. That's the part of the light spectrum that picks up warmth. Infrared telescopes like NASA's Spitzer, ESA's Herschel, or the more recent James Webb Space Telescope have opened up a new way of seeing space. They can spot brown dwarfs, cold planets, and distant dust clouds. But detecting Oort Cloud objects is a much harder task. The objects are small, far away, and spread thin. Their warmth is barely there. Even James Webb, one of the most powerful space observatories ever built, likely can't pick out individual Oort Cloud bodies. But maybe, just maybe, it could detect their combined glow, if there are enough of them. This is called background emission. If the Oort Cloud holds trillions of icy bodies, and each one gives off the tiniest trace of infrared light, that faint warmth could add up. A glow that fills the sky evenly, not from any one place, but from a spherical shell all around us. If we can subtract all the known sources of infrared light from our data, stars, galaxies, zodiacal dust, what's left might be the echo of the Oort Cloud. There's another approach, one that doesn't look for light at all. It looks for shadows. This technique is called occultation. When a small object in space passes in front of a star, even just for a split second, it blocks a tiny bit of starlight. The star dims, then returns to normal. This flicker can reveal the size and position of the object, even if we never see it directly. Occultation has already helped astronomers discover small moons, rings around distant objects, and even new members of the Kuiper Belt. Applying the same method to the Oort Cloud is a bigger challenge. The stars must be watched very carefully. The dimming is tiny, and it doesn't last long, but with enough stars and enough time, it might work. Telescopes like the Vera C. Rubin Observatory will soon be watching wide areas of the sky with great speed and detail. If an Oort Cloud object passes in front of a star, the telescope might catch it, just for a moment. Even better would be to use space-based observatories in tandem. If two or more satellites far from each other see the same flicker, they can compare data and calculate the path of the hidden object. This would give us its speed, size, and even its rough distance. Doing this once would be impressive. Doing it many times would begin to outline the invisible shape of the Oort Cloud. There's also the idea of gravitational microlensing. This is when an object's mass bends the light of a background star, not by blocking it, but by warping it slightly. We usually use this method to find planets or black holes. But in theory, it could also work for large Oort Cloud objects, especially ones with a little more mass, maybe even mini-planets that ended up out there. Some scientists have also talked about building swarms of small spacecraft, each equipped with sensitive sensors. They wouldn't need to travel all the way to the Oort Cloud. They could stay in the outer solar system, beyond Neptune and Pluto, and wait. If one of them ever detected a faint impact or gravitational tug, something small passing nearby, it could be our first up-close encounter with a true Oort Cloud body. But all of these methods rely on technology and patience. The Oort Cloud isn't going anywhere. It's been out there for billions of years, and it will stay there long after we're gone. Our biggest enemy isn't the distance, it's the quiet. The objects out there don't make much noise in any sense. They don't shine, they don't move quickly, and they don't give off any signals. One of the most exciting developments may come from artificial intelligence. Modern sky surveys gather massive amounts of data, so much that no team of humans can scan it all. AI programs, trained to spot patterns or strange movements, might one day pick out a candidate object from the far reaches of space. It could flag a subtle occultation event. It could track a motion too slow to notice otherwise. What would go unseen by eyes and unnoticed by code could one day be flagged by a machine built for that very purpose. There's another idea that seems almost fantastical, but isn't. It's the use of solar sails or other advanced propulsion methods to send lightweight probes directly toward the outer solar system. If such probes could reach even a fraction of the distance of the Oort Cloud in a human lifetime, they could act as scouts, looking, listening, sampling. One concept, proposed by Breakthrough Starshot, involves tiny spacecraft pushed by powerful lasers. Most of their designs aim at stars, but the same technology could be pointed closer to home. The Oort Cloud would be a good place to start. For now, though, the Oort Cloud remains a dream and a calculation. Science moves toward proof, but sometimes it walks slowly. The quest to detect the Oort Cloud directly is like trying to find the edge of a shadow. You can't touch it, you can't always see it, but you can tell it's there, just beyond your reach, waiting to be revealed. Our tools are getting better. Our questions are becoming sharper. We're watching the stars more carefully than ever before. And the Oort Cloud may not be invisible forever. One day it might finally show its face. Not all at once, but piece by piece. A flicker here, a glow there, a whisper that becomes a voice. And then, finally, we will have seen it. Frozen clues. What a sample return from the Oort Cloud could reveal. If we could reach out into the deep cold of space and collect even one tiny fragment from the Oort Cloud, it could change how we understand everything that came before us. While planets grew, merged, or broke apart, the icy bodies that would become part of the Oort Cloud just drifted into the far cold, waiting. A sample return mission would mean going all the way out to where the solar system fades into interstellar space, finding one of these objects, probably only a few kilometers across, and landing on it. Then, somehow, the spacecraft would need to collect material, launch itself back toward the Sun, and return the cargo to Earth. Daunting though that may seem, we've already done similar things, though on a smaller scale. Japan's Hayabusa missions brought back pieces of asteroids. NASA's OSIRIS-REx brought back material from Bennu, but those targets were nearby, relatively speaking. The Oort Cloud is not. So engineers and scientists imagine other ways, perhaps ion drives, nuclear-powered engines, or laser-propelled sails. A more likely goal in the near future is to study comets that come from the Oort Cloud, instead of going all the way to it. Even these brief visits give us a chance to learn. When a comet like that enters the inner solar system, its icy surface heats up and begins to release gases and dust. That material can be studied from Earth or by spacecraft that fly by. NASA's Stardust mission collected dust from the coma of Comet Wild 2. Probably not an Oort Cloud object, but still a step in the right direction. A future mission could do the same with a comet that we know came from the far cloud. or better yet, land on it. What would we learn from such a sample? First, we'd learn about the building blocks of the solar system. The dust and ice in these objects could contain elements and molecules that were present in the solar nebula. Some of these materials may have changed very little since then. They might tell us what kinds of chemicals were common in the earliest days, before the planets had even formed. They could help answer questions about where the solar system formed and how it gathered the ingredients that would later lead to life. Some scientists also believe that objects like those in the Oort Cloud might have delivered water and organic molecules to Earth. The early Earth was hot, volcanic, and probably dry. But over time, comets and asteroids bombarded the surface. Many of those comets may have come from the Oort Cloud. If they carried water ice, and many do, then they may have helped fill our oceans. If they carried carbon-based molecules, like amino acids or alcohols, then they might have helped lay the ground. A sample could tell us what kinds of compounds were inside these icy visitors. It could show whether the story of Earth's life really began in the cold dark beyond Neptune. There's also the idea that some of these ancient objects contain materials from other stars. A sample from the Oort Cloud might carry fingerprints of these foreign worlds, isotopes that don't match the Sun, minerals that formed in very different conditions. It could be a record of not just our story, but the galaxy's. Another possibility, even more speculative, is the detection of complex organic molecules, maybe even simple prebiotic compounds that resemble the building blocks of RNA or DNA. This wouldn't mean life began in the Oort Cloud, but it would suggest that the ingredients for life are scattered throughout space, that they might form naturally even in the dark, cold void. If life's parts are common, maybe life itself is too. But if we brought such a sample back, how do we protect it? How do we make sure it doesn't get contaminated, either by Earth or by us contaminating it? Missions like OSIRIS-REx and Stardust use sealed containers, clean rooms, and specially trained teams to handle return material. A sample from the Oort Cloud would demand even stricter care. We'd want to study it slowly, carefully, and probably in stages. Some would go to labs around the world. Some would be preserved for future scientists, using tools we haven't even invented yet. We might also find surprises. Past missions have returned materials that didn't match predictions. Stardust brought back minerals that had formed in high temperatures, strange, considering its target was a cold comet. That led to new ideas about how materials move inside solar systems. A sample from the Oort Cloud could challenge what we think we know. It could force scientists to rewrite models of how the planets formed and how matter moved through space. Imagine opening a sealed container, knowing that what's inside has never seen sunlight since the solar system began. It's like hearing a whisper from the very edge of time. Someday, perhaps not too far in the future, we might bring home the first true piece of that frozen, distant cloud. A small, silent fragment of our past, and maybe a clue to our beginning. What if the Oort Cloud doesn't exist? Reimagining the source of long-period comets. What if the Oort Cloud doesn't exist? What if all those long-period comets, the ones that suddenly appear from deep space with no clear pattern, are coming from somewhere else entirely? It's not a comfortable question, but science needs questions like this. They help test ideas. They keep old theories honest. The Oort Cloud is a useful explanation, but it's still a model, an idea that fits the data, not a proven structure. If future missions never detect it, if samples never come, or if comet data starts pointing in strange directions, we may have to face the possibility that something else is going on. One of the first things to consider is where else long-period comets could come from. If we remove the Oort Cloud from the picture, we still need a source. These comets don't just appear from nowhere. They follow long, stretched-out orbits, and many of them are seen for the first time as they dive toward the Sun. Their orbits suggest that they started very far away. Without the Oort Cloud, the solar system needs another reservoir. It needs another deep freezer full of icy bodies. One idea is that there could be a flatter, more stretched-out disk of icy objects, tilted at a strange angle to the rest of the solar system. This kind of structure might not be spherical like the Oort cloud is supposed to be. It could be more like a warped ring or a thick band, shaped by gravity and time. Maybe it was formed by the same events that built the Kuiper Belt and the scattered disk. Maybe it's a leftover structure from the solar system's early years, disturbed by the gravity of passing stars or rogue planets. There's also the possibility that some comets don't come from any long-term storage zone at all. Some astronomers have asked whether interstellar space itself could deliver icy objects. This idea got more attention after the discovery of Oumuamua in 2017 and Comet Borisov in 2019. Both were moving too fast to be bound to the Sun. They were just passing through, visitors from other star systems. If objects like these can reach us, maybe some of the long-period comets we've seen are actually from beyond our solar system, misidentified as local. As the solar system moves through the galaxy, it passes through areas filled with drifting debris. If a piece of ice or rock floats near enough to the Sun, and its speed and direction match just right, the Sun's gravity could grab it. The object would switch from a free floater to a member of the solar system, looping in on a long, narrow path. Over time, that path could shift until the object dives inward and becomes visible from Earth. But for that to work, the capture process would need to happen a lot. And there's not yet enough evidence to show that such a high number of comets could be explained by capture alone. Still, it adds uncertainty. It shows that other sources exist. Another theory looks inward instead of outward. Some researchers have suggested that the solar system's own structure may be more chaotic than we thought. Maybe interactions between the planets and the Kuiper Belt are more complex. Maybe large bodies on the edge of the system, like the suspected Planet 9, could be flinging objects into long-period orbits from a zone much closer than the Oort cloud. These interactions would be rare but powerful, enough to launch comets toward the inner solar system without needing a distant cloud at all. Then there are models that point to earlier times. In the early solar system, there were many more icy bodies and planetesimals than there are today. The system was messy, violent, and full of movement. Some scientists argue that many of the comets we now see may have been launched into strange orbits billions of years ago and have simply been circling ever since. If those paths are stable enough, then these comets don't need a reservoir. They are the leftovers of an ancient explosion of movement. But each of these ideas has problems. Some don't explain the number of comets we see. Some don't match the patterns in their orbits. Some require events that are very rare or that only work under very specific conditions. That's one reason the Oort cloud remains such a powerful idea. It neatly explains the data. It predicts the shapes of comet orbits. It gives the solar system a boundary and a history. If the Oort cloud isn't real, then our picture of the solar system shrinks. It becomes more compact and less mysterious. It also means that some of our theories about how the solar system formed and evolved would need to be re-examined. The flinging of icy objects by Jupiter and Saturn, the shaping of the outer regions by stellar encounters, the shielding of the inner planets from dangerous impacts. Many of these ideas depend on the Oort cloud being real. There are also cultural consequences. The Oort cloud is one of those rare scientific concepts that has entered popular imagination. It shows up in documentaries and books. It's become a symbol for the unknown. If that frontier isn't real, it changes how we think about our place in the universe. The line between us and the stars becomes more vague, more open-ended. The edges of our home become harder to draw. Still, even if the Oort cloud turns out to be just a placeholder, a name for something we don't fully understand, it doesn't mean the search ends. It means we dig deeper. We ask harder questions. We build better tools. And maybe, in doing so, we discover something even more surprising. Science is full of ideas that were once solid but later replaced. The ether, the steady-state universe, the ninth planet that turned out to be Pluto and then wasn't. The Oort cloud may someday join that list, or it may prove to be real after all, hiding in the cold and waiting to be confirmed. But for now, it stands as one of the biggest unanswered questions in planetary science, an idea too distant to touch, but too useful to ignore. The ultimate mission. What would it take to visit the Oort Cloud? Right now, our fastest spacecraft take decades just to reach the outer planets. To reach the Oort Cloud in a human lifetime, a probe would need to travel far faster than anything we've ever built. Some scientists have suggested speeds of at least 20 to 30 AU per year. At that rate, a mission could reach the inner Oort Cloud in about 70 to 100 years. That's still a long wait, but it's not impossible. Future technology might bring that travel time down even further. One idea that gets discussed a lot is solar sails. These are large, thin sheets that use the pressure of sunlight to push a spacecraft. The farther from the sun the probe travels, the weaker that push becomes. But if a sail is large enough and the spacecraft is light enough, it can build up speed over time without using fuel. Solar sails have already been tested on small missions like Japan's Icaros and the Planetary Society's light sail. A bigger, more advanced version could give us the long-lasting thrust needed to reach deep space. Another idea is nuclear propulsion. This could mean either nuclear electric engines or nuclear thermal rockets. These types of systems could offer stronger, steady acceleration than chemical rockets. They would allow a spacecraft to keep speeding up even after it left the inner solar system. There are technical and safety issues with nuclear-powered flight, but several space agencies have started looking at it again, especially for future missions to the outer planets and beyond. Some more daring ideas include fusion-powered spacecraft or even beamed propulsion, where lasers on Earth or the Moon push a tiny probe using concentrated light. But these ideas are still experimental. They would take major breakthroughs in materials, guidance, and energy systems. Besides speed, the next challenge is power. The sun gets dim very quickly as you move away from it. By the time you reach even Pluto's distance, sunlight is too weak to power normal solar panels. At Oort Cloud distances, sunlight is just a faint glow, thousands of times weaker than what we get on Earth. That means any spacecraft would need its own power source. Right now, we use radioisotope thermoelectric generators, or RTGs, like the ones on Voyager and New Horizons. They work by turning heat from radioactive decay into electricity. But RTGs don't last forever. After a few decades, their power output drops off. A mission to the Oort Cloud would need a power source that can last at least a century, and maybe more. That's a huge engineering problem. It might require better RTGs or something entirely new, like miniature nuclear reactors. These systems would need to be safe, lightweight, and able to handle extreme cold for decades without repairs. Right now, even Voyager 1 takes more than 22 hours to send a signal to Earth. The farther a spacecraft gets, the longer the delay. A probe in the Oort Cloud would take weeks to transmit a message, even at light speed. The signal would also be very weak. We'd need huge antennas and sensitive receivers on Earth just to hear it. And the spacecraft would need enough power and the right kind of transmitter to send anything back at all. Navigation is also tricky. Once a spacecraft leaves the inner solar system, there are fewer landmarks to help guide it. It can't use planets or moons for course corrections. The Oort Cloud is made up of tiny icy objects spread out over an enormous volume of space. Hitting one of them by accident would be a disaster. Finding one on purpose would be like trying to hit a single grain of sand drifting in the ocean. The probe would need to be able to detect small objects on its own, or it would need detailed instructions sent from Earth. Either way, the system would have to work perfectly over many decades. Even if we solved all those problems, there's still the question of what the mission would do once it got there. Should it just fly by and take pictures? Should it try to enter orbit around one of the icy bodies? Should it collect samples and try to return them to Earth? Each of these goals adds complexity. A flyby is easiest, but it gives only a brief look. Orbiting requires slowing down, which is hard to do so far from the Sun. A sample return would be the hardest of all. It would need a way to bring material back across billions of kilometers through deep space, and survive re-entry into Earth's atmosphere. Still, some scientists believe it can be done. They argue that a probe to the Oort Cloud would be the next great leap in space exploration. To make such a mission happen, we would need long-term planning. We would need to design spacecraft that last for a century or more. We would need international cooperation, steady funding, and a vision that stretches beyond human lifetimes. The data it sends back might be studied by future generations, but the rewards could be enormous. The Oort Cloud, if it exists, is the most distant part of our solar system. It's the last great unknown. A mission there would be the farthest journey ever made by humans, or at least by our machines. It would be a statement of our unwavering curiosity, a way of saying that we want to know, even if the answers are frozen in the dark, waiting at the edge of everything. Warp drives, fusion sails, and hibernation, theoretical tech to breach the cloud. Getting to the Oort Cloud, with today's technology, already seems like a nearly impossible challenge. But if we look ahead, far beyond what we can build right now, we find a different world of ideas. These are not just upgrades to our current engines. They are completely new ways to think about space travel. If any of them ever become real, they could take us not only to the Oort Cloud, but far beyond it, maybe even to other stars. Unlike regular rocket engines, which burn fuel quickly and get a short burst of power, a fusion engine would use the same process that powers the sun. At the core of this idea is the fusion of light atoms like hydrogen into heavier ones like helium. When this happens, a huge amount of energy is released. If we could harness that energy in a controlled way, we could build engines that run for a long time and push a spacecraft to incredible speeds. Fusion engines would not be easy to build. We haven't even mastered fusion power for use on Earth yet. But research is ongoing. Projects like the Princeton Plasma Physics Lab and international experiments like ITER are working towards stable fusion reactions. In space, a fusion rocket could keep accelerating for years. It wouldn't burn out like a chemical rocket. It would slowly build speed, eventually traveling many times faster than Voyager or New Horizons ever did. One concept, called the Daedalus Project, was first proposed in the 1970s. It imagined using fusion pellets, tiny bits of fuel ignited by electron beams. A spacecraft powered this way could travel about 10% the speed of light. That's fast enough to reach the inner Oort Cloud in a few years, not decades. Updated versions of this idea, like the Icarus project, have continued to refine the math and the engineering behind it. The challenge is not just the engine, but the materials. The craft would need to handle high temperatures, radiation, and stress over long periods. It would also need a way to aim and adjust course with almost no help from Earth. Another futuristic idea is the fusion sail. This is something like a cross between a solar sail and a fusion engine. The concept involves a spacecraft carrying small fusion charges or using an onboard fusion reactor to heat plasma. That plasma would then be pushed out of the back of the ship, giving it thrust. Unlike regular engines that shoot out exhaust, the fusion sail might spread its thrust out over a large magnetic field, basically riding a wave of plasma and energy. This would reduce wear on the spacecraft and might allow for smoother, faster travel. For many of these missions, speed isn't the only problem. Time is. Even with a fusion-powered craft, a journey to the outer edge of the Oort Cloud might take longer than what a human body can handle. And that raises a big question. What about the crew? Could we ever send people on such a mission? Not unless we solve the problem of surviving long space journeys. That's where another idea comes in: hibernation or suspended animation. The basic science isn't impossible. Some animals, like bears or frogs, can slow their metabolism during winter. Their heart rate drops, their body temperature cools, they use very little energy. Some scientists think we might someday do the same with people. One way to do this could involve cooling the human body to just above freezing and slowing all body functions. The person would be kept alive, but not awake. Their cells would barely be working. Medical teams have already tried something similar in short-term trauma cases, cooling patients after major injuries to reduce brain damage. The next step would be finding a way to do this safely for months or even years. If it worked, hibernation could solve many problems. It would reduce food and water needs. It would lower stress and boredom on long missions. And it might protect the body from radiation, since hibernation may help the body repair DNA damage more efficiently. But there are risks. What if something goes wrong while the crew is asleep? What if the hibernation process isn't perfect and leads to long-term health problems? These are all questions that would need to be answered before sending humans into deep space. Of course, many scientists think that our first trips to the Oort Cloud and beyond should be done with robots. Machines don't need air, food, or sleep. They can last longer and handle rougher environments. But robotic missions would need some level of artificial intelligence to make decisions on its own. It couldn't wait weeks or months for commands from Earth. It would need to steer, scan, and even fix itself without help. An AI-powered spacecraft could search for targets in the Oort Cloud, adjust its path, and send back only the most important data. It could study objects as it passed them, or even land briefly to collect samples. In the future, we might not just send one big spacecraft. We might send dozens of small smart probes, each able to explore different parts of the Oort Cloud and share information with each other. If we push the imagination even further, we get to warp drives. This is the idea that space itself could be bent or folded to move faster than light. The most famous version is called the Alcubierre drive, named after a physicist who showed, at least on paper, how space could be stretched behind a spacecraft and compressed in front of it. This wouldn't move the ship faster than light, but it would move the space around it, so the ship would appear to travel at super speeds. There's no proof that this can work. It would take enormous amounts of energy, possibly more than exists in the whole universe. It might need exotic matter with negative mass, something we've never seen. Even if warp drives never become real, they push us to think about the limits of physics and how we might someday break them. These dreams, fusion sails, AI scouts, hibernation pods, and space-bending engines, might sound far off. And they are. But all of today's space missions started with ideas that once seemed just as impossible. A century ago, even getting a rocket into orbit was seen as fantasy. Now we have rovers on Mars and telescopes in deep space. The journey will be long, the odds will be tough, but the goal will keep pulling us forward. Have we already sent the first artifacts that will touch the Oort Cloud? When scientists and engineers built the Voyager spacecraft, their minds were focused on the planets. The mission was meant to visit the outer worlds and take close-up pictures we had never seen before. They designed the spacecraft to last long enough to fly by these planets, send back the data, and then drift off into space. But what they might not have fully expected was that, almost 50 years later, Voyager 1 and Voyager 2 would still be out there, still moving, and still telling us something about the edge of our solar system. Voyager 1 passing the heliopause was a huge moment. But if the solar system were shrunk to the size of a beach ball, the planets would fit inside a pea and the Oort Cloud would still be several meters away. That gives you a sense of just how far away it really is. At its current speed, it would take more than 300 years just to reach the edge of the cloud, and possibly thousands of years to pass through it. Voyager 2, moving a bit slower and in a different direction, would take even longer. Still, both spacecraft are on paths that will eventually lead them into the Oort Cloud, assuming nothing stops them. If they do make it into the Oort Cloud, what will happen to them? Probably nothing. The Oort Cloud is huge, but it's not crowded. The objects in it are spaced out over vast distances. Even though the cloud may contain billions or trillions of icy bodies, they are so far apart that the Voyagers will almost certainly drift right through without hitting anything. And since they don't have engines to steer or slow down, they'll just keep going. They are not alone. Other spacecraft are also heading in that general direction. Pioneer 10 and 11, launched before the Voyagers, are also moving away from the Sun. Their signals were lost years ago, but their bodies remain on course. New Horizons is also now moving into the outer solar system. It may follow a path that, over time, brings it near the Oort Cloud as well. But all of these spacecraft face the same problem: time. It takes thousands of years to reach the Oort Cloud, and none of them were built to last that long. Their RTGs will lose strength over time. Most are expected to run out of power within the next decade. Once that happens, the spacecraft will go dark. They will become dead relics, drifting quietly through space. Even in that state, though, they are important. They are physical proof that humans can build things that last longer than a civilization. They also help us think about what it would take to build something better, something that could survive the journey and study the cloud from within. Could a future spacecraft be designed to actually enter the Oort Cloud and stay active? Maybe. It would need better power systems. It would need insulation, shielding, and the ability to handle complete darkness. For now, though, the Voyagers are the best we have. They are simple machines by today's standards. They use technology from the 1970s. Their memory is tiny. Their processors are slower than a basic calculator. But they still carry our hopes with them. They may very well be the first artifacts to ever enter the Oort Cloud, even if it takes generations for that to happen. If we ever do send a real mission to the Oort Cloud, it will owe something to the Voyagers. Those old spacecraft showed us how long such journeys might take, and yet despite that, they're not beyond our reach. Bit by bit, artifact by artifact, we're already on our way. Can a human ever physically reach the Oort Cloud in a lifetime? Let's say that we want a mission to reach the Oort Cloud in 50 years. That might sound long, but it's about the upper limit of a working life for most people. If someone signed up at 20, they'd be 70 by the time they arrived. To pull this off, the spacecraft would need to move about 10 times faster than anything we've ever launched. It would need to cruise at more than 150 kilometers per second and sustain that speed for decades. That kind of speed isn't impossible in theory. There are ideas like nuclear fusion drives or antimatter engines that might be able to get close to that one day. But even if we did, it wouldn't solve the other problems: radiation, isolation, power, food, and many more. Human life isn't designed for travel at those kinds of distances. In space, everything is limited. Supplies have to be carried or created. Protection from cosmic rays and solar storms becomes more critical the farther you get from Earth's magnetic field. And then there's the psychological weight of the journey. Months turning into years, years into decades, and no planets nearby to stop at. The void of space is more than empty. It's crushing in its scale. A trip to the Oort Cloud would make even Mars missions look like short vacations. At least with Mars, you can talk to Earth with only a few minutes delay. In the Oort Cloud, that delay could stretch to days or even weeks. Communication would become more like sending mail than holding a conversation. That changes how a crew would live and make decisions. They couldn't wait for answers. They'd have to handle emergencies on their own, with no help from Earth. Then there's the return trip. Even if you could reach the Oort Cloud in a lifetime, you'd be unlikely to come back. A one-way journey is much more practical. It means fewer supplies, less fuel, and simpler engineering. But it also raises hard questions. Who would go, knowing they'd never return? What kind of person would take that on? Not just the physical risk, but the emotional cost of leaving Earth behind forever. For now, the only real solution would be to stretch the limits of life itself. That's where ideas like hibernation or suspended animation come in. If it worked, a crew could sleep through most of the journey. That would help with food, boredom, and even aging. Still, no human has ever been put into a long-term stasis and woken up. We've seen some success in animals and in slowing down certain injuries in hospitals. But turning that into a working system for decades of space travel is a massive challenge. And it still wouldn't remove the risks: radiation, equipment failure, and the simple fact that a lot can go wrong in 50 or 100 years. There's also the question of what the crew would even do once they arrived. The Oort Cloud isn't like a planet. It's a vast spread of scattered ice and rock. so spread out that you might travel for years without seeing anything close enough to study. A human mission would need to be lucky, or extremely well guided, to even find a target worth visiting. Without that, the mission becomes more about the journey than the destination. That's not to say it couldn't happen someday. Human beings have always pushed limits. We crossed oceans when the maps were blank. We sent balloons into the sky before we understood flight. We walked on the moon with computers less powerful than a modern smartwatch. The drive to explore is deep in our history. In the distant future, it's possible that we won't have to ask if a single person can make the journey in one lifetime. Maybe humans will live longer. Maybe we'll be born in space, raised on moving ships, with lifespans stretched by medicine or genetics. Maybe entire families will live and die on interstellar craft, never setting foot on a planet. In that world, reaching the Oort Cloud might be just the first step, not the final one. But today, that's still a dream. If you ask whether a person born now could train, launch, and physically reach the Oort Cloud before they die, the answer, by everything we know, is no. The technology isn't ready. We're just beginning to leave the neighborhood of our planets. The Oort Cloud is more like the edge of the forest, still far beyond the first trees we've stepped into. Will the Oort Cloud become our final physical limit? In the vastness of space, there are no fences, no lines drawn in the stars that say this far and no farther. But in practice, we do find edges. We find points where things become so difficult, so slow, so far away, that they start to feel like barriers. The Oort Cloud may one day become one of those places, a soft border at the edge of what we can physically touch, explore, or claim. Not because it was meant to be a wall, but because the distance, time, and energy it demands may outpace what humans or machines can deliver. The Oort Cloud surrounds our solar system like a ghostly shell. If you were looking down at the solar system from above, the Oort Cloud would look like a faint bubble surrounding everything we know, our planets, our probes, our light. That bubble could become our cosmic horizon, not a solid line, but a limit in another way, a point past which missions don't return, or where signals grow too weak, a place that marks the last outpost of human reach. Space is already hard. Even reaching Mars is a challenge that takes years of planning, engineering, and patience. The outer planets are much farther, and every step beyond multiplies the difficulty. A journey to the Oort Cloud would stretch out over decades or even centuries. For a machine, it's possible in theory. For humans, the challenge becomes about something bigger than engineering. It becomes about what an individual is willing to sacrifice. Eventually, we may get there. We may build probes tough enough to drift through the Oort Cloud and send back pictures, data, and dust samples. But even then, the cloud may still mark the edge. Not because it's the hardest thing we've ever tried, but because the return on effort may not keep pace with our needs. Every new mission has to fight for funding, for interest, for value, and the farther you go, the harder that fight becomes. Beyond that cloud lies the open sea between stars. It's not empty, but it's quieter, darker. The density of matter drops. Out there, we stop being in the solar system at all. We become part of the galaxy. For a long time, space travel has been about steps. First the Moon, then Mars, then maybe the moons of Jupiter or Saturn. Each goal builds on the one before it, but the Oort Cloud breaks that pattern. It isn't a world to land on. It isn't a gas giant with rings. It's not even a single destination. That makes it different from any goal we've aimed for before. And that's part of the problem. It's hard to see it, hard to define it, and that makes it hard to chase. Still, humans don't always need certainty. Sometimes it's enough to know there's something out there. The Oort Cloud represents the edge of our domain. If we ever cross that invisible border, it means something. It means we've reached the true boundary between solar system and galaxy. It means we've touched something that formed with the planets, that drifted in the deep freeze of time for billions of years. But it may also be the place where we stop. Not forever, maybe, but for a long time. The energy it takes to go beyond may not be worth the cost, at least not in the way we think about travel today. Even if we send machines past it, the Oort Cloud may be the last stop before everything else fades into the background. There's something poetic about that idea, that we could one day say we've reached the outermost layer of the solar system, that we've stood on the final shore, looked out into the darkness, and left a flag or a signal to show we were there, not as conquerors, but as explorers. Even if we never touch it, the Oort Cloud gives us something that all explorers need, a frontier, something to aim for, even if it takes more than one lifetime to get there. And maybe that's enough. Maybe that's the point. But there's also something humbling, because space doesn't care where we draw the line. It doesn't give us limits. We make them ourselves. The Oort Cloud may be the last place we can visit with current thinking, but maybe that just means we need to think differently. If we change how we build, how we move, how we live, then maybe the Oort Cloud becomes just another step. But if not, if we stay as we are, then it may stay out there as a quiet reminder of our limits. A simulated skybox. Could the Oort Cloud mark the boundary of a simulation? Simulation theory suggests that everything around us, from atoms to galaxies, could be part of a giant digital model. According to this idea, what we think of as real could be something like a very detailed program running on a system far beyond our understanding. And within that possibility, the Oort Cloud has drawn special attention. It feels like a limit. It acts like a soft wall around our system. We've never gone past it. It might just be the way the solar system is built, but it might also be the place where the model ends. In many video games, there's something called a skybox. It's the outer shell that creates the illusion of a world. It shows stars or clouds or distant mountains. But it's not real depth. It's a painted background that tricks the eye. You can't go past it. It just tells the player, this is the edge. Some people wonder if the Oort Cloud might be like that, a rendered zone that marks the outer limit of what needs to be simulated. This idea is strange, but not completely random. It comes from a real pattern in how the Oort Cloud behaves. First, it's incredibly far away. Second, it's too dim and sparse to be seen directly with current tools. Third, it gives us just enough indirect evidence, like long-period comets, to believe it's there. That balance between evidence and invisibility fits well with the idea of a system designed to look real from the inside, but not waste energy simulating too much detail where no one can go. In a simulation, resources are often saved by not fully rendering distant places. If nothing is looking at them, there's no need to keep all the details active. The same way a game doesn't fully draw a mountain until the player gets closer. A simulated universe might only fill in what's needed. The Oort Cloud could be a zone that stays fuzzy on purpose, just enough data to explain what we observe, but not much more. There's also the behavior of comets. Long-period comets seem to come in from random directions, as if they're falling in from a sphere. That matches what we expect from the Oort Cloud. But in a simulation, that randomness could be a feature. It would keep things interesting. It would make the system seem natural, while still operating inside a set of rules. A comet that appears from deep space might be like a randomized event, something to test or reset a part of the system. The Oort Cloud orbits happen on such long timescales that we'll never watch them play out. The full orbit of a typical Oort Cloud object is far longer than all of human history. That means no one inside the system will ever see the whole thing. In a simulation, that would be a clever way to save memory. You include a process that looks active, but it never needs to complete. It just creates the appearance of complexity. The Voyager spacecraft's power will run out long before they reach the cloud. In a simulated world, this kind of limit might act as a barrier. You let the explorers get close, but not close enough to prove or disprove the structure. It keeps the illusion alive without showing the backstage. It's not just the physical distance, it's the way the Oort Cloud seems to avoid interaction. It doesn't light up. It doesn't form moons or planets. It just waits in silence. It's real enough to study, but unreachable enough to stay mysterious. For believers in simulation theory, this kind of pattern is a clue. The Oort Cloud could be part of the architecture, not just an object but a structural edge, where inside becomes outside and beyond it, the system stops running full physics. Like a fog wall in a game, it says, "You can't go this way." It's there, but not there. It's part of our models, but not part of our direct experience. And that leaves a strange gap in how we understand space. We don't like empty maps. We don't like loose ends. When we see a strange pattern, we try to connect it. We try to make sense of it. The simulation idea might be one way to do that. It takes the unknown and turns it into a boundary, a kind of intelligent limit. And if the Oort Cloud were part of a simulation, what would that mean? Would it change how we study space? Would it mean we should stop exploring, or that we should try harder to test the edge? Maybe we'd build missions not just to sample ice, but to probe the boundary itself, to see if anything shifts, flickers, or glitches, to test if reality itself has seams. For now, the idea remains just that, an idea. The Oort Cloud might be exactly what we think it is, a cold, slow drift of early solar system debris. But it also holds a place in the far edge of our imagination. Not just the edge of the system, but the edge of belief. A place where science, theory, and wonder all start to blur. If we're living in something like a simulation, then the Oort Cloud could be one of the best places to look for signs. It's the kind of place a simulation might build just well enough to pass the test, and no more. Until we find a way to go there or see it directly, the question stays open. Not just what the Oort Cloud is, but what it means. How would one prove the universe is simulated, starting at the Oort Cloud? At first glance, the idea seems impossible. How could anyone prove that the entire universe is a simulation? How would we even start? Most people imagine it would take some huge discovery, like finding a control panel floating in space, or a line of code hidden in the stars. But if the universe is being simulated, like a vast digital world, then its edges might hold clues. And one of those edges could be the Oort Cloud. Simulation theory is built on a simple idea. If it's possible to build a simulated world full of thinking beings, then perhaps it has already been done, maybe more than once. If we're inside one of those simulations, there could be signs, subtle patterns or limits placed by whoever created it. Finding those signs is hard, but not hopeless. One idea is to look for limits in resolution. In a video game, the world becomes blurry or simple when you get far from the player's main location. The system doesn't waste power simulating full details where the player can't go. Could something similar happen at the solar system's edge? The Oort Cloud, by nature, is hard to observe, but if we could somehow detect small patterns in how light passes through that zone, like from distant stars shining behind it, we might notice something strange. Maybe the distribution of dust or particles wouldn't follow normal physics. Maybe there would be a minimum level of detail, like a pixel limit in a 3D world. If the resolution of the universe starts to break down at long distances, or if reality behaves differently when no one is looking directly at it, that could be a clue. Another possible test involves randomness. In a truly natural universe, quantum effects are random but follow probabilities. But in a simulation, randomness might be faked. It might be based on algorithms that produce results which only seem random. Some physicists believe that with enough data, we might be able to tell the difference. For example, if the arrival times or paths of long-period comets show patterns that don't match real chaos, but instead repeat in odd ways, someone might suspect that a deeper structure is at play. There's also the idea of gravitational anomalies. Some spacecraft, like Pioneer 10 and 11, showed slight deviations from expected paths. These Pioneer anomalies were later explained by heat emission, but they sparked interest in how we check the laws of gravity in deep space. If a future mission to the Oort Cloud noticed tiny, consistent deviations in gravity, something that didn't fit Newton's or Einstein's models, It could hint at a hidden framework beneath the surface. A grid, a clock rate, a set of artificial rules. The simulation might also try to conserve resources in clever ways. If we sent a probe into the Oort Cloud and it disappeared, not due to damage but into some form of information void, it would raise questions. What if we kept trying to observe an object but couldn't lock onto it? Or if our instruments behaved differently depending on whether anyone was watching the data? In a simulated world, attention might be part of the system. Things might only fully exist when someone looks at them. That leads to experiments with observer effects. In quantum physics, the act of measurement can influence the outcome. Most scientists agree this is a real part of nature, but in simulation theory, it might be baked in, an intentional shortcut. Maybe nothing at the edge of the solar system becomes fully real until we send sensors. A test would involve comparing data from passive instruments, just listening or watching, versus active ones, sending energy, touching things. If results change dramatically based on the method, it might be evidence that the system responds to interaction. Other thinkers have suggested looking for processing errors. In some games, if you move fast enough or push the system in strange ways, you get glitches. Objects fall through the floor, or distances become warped. If we ever sent a craft toward the Oort Cloud at extreme speed, and it reported strange physics, like changing time rates, repeating signals, or impossible angles, it could be a kind of tear in the rendering. These would be hard to fake in a real, consistent universe, but could happen in a system built on rules that stretch only so far. A bolder idea is to test the limits of physics constants. Things like the speed of light, the charge of an electron, or Planck's constant seem universal. But in a simulation, those values might be adjustable. What if we found that one constant was very slightly different in the outer solar system than it is near Earth? If we could measure the same property in two places, say, a type of radiation reflection, and find that the math didn't add up, that would be deeply unsettling. It might suggest a system that wasn't truly uniform. Some scientists have proposed that we search for embedded messages. If we were programmed beings, the builders might have hidden information in the cosmic background, in numbers, structures, or even comet paths. It would be like an artist signing their name in the corner of a painting. This idea is hard to test and may be impossible to prove. But some have looked at things like the digits of mathematical constants or the geometry of the universe itself to see if they contain patterns that seem too perfect. The Oort Cloud might act as a kind of cosmic canvas for such a message. Not because the message is there in plain sight, but because it's a zone where the simulation wouldn't need to work as hard. It might be sloppier. Or it might be where the system places extra clues, knowing that only advanced civilizations would ever get close. For now, we can't go there. But the mystery remains. If we ever want to test whether our universe is real in the way we think, the far edge might be the best place to start. If the simulation is real, what role does the Oort Cloud play? In computer systems, boundaries are everywhere. They help manage data. They divide spaces into zones so that processes don't mix. They form firewalls, buffers, or memory partitions. If the universe is a kind of program, then it might need zones too, places that keep the active parts of the simulation separate from the parts that are not meant to be directly accessed. The Oort Cloud might be one of those zones. It could be a buffer zone, a place where the simulation gradually lowers the level of detail. Closer to the Sun, the simulation might need to render things in high resolution: planets, weather, people, machines. All of that requires more processing. But far from the Sun, where not much happens, the system might reduce its effort. The Oort Cloud could be the edge of where full simulation ends and background processes take over. A kind of visual fog or static, like the edge of a digital map in a video game. In that case, comets coming from the Oort Cloud might be like test probes. Not from us, but from the system itself. Maybe they're how the simulation introduces randomness, checks internal rules, or stirs up the inner solar system at regular intervals? If so, then what we call long-period comets could be part of a larger algorithm, one that balances the inner solar system by injecting these icy visitors from time to time. Or maybe the Oort cloud is more like a firewall. In a digital system, a firewall prevents access between one part of the system and another. It stops programs or users from seeing things they're not meant to see. If there's anything beyond the Oort cloud that we aren't supposed to interact with, then that cold, distant shell could be the protective layer. It doesn't have to be made of fire or metal. In a simulation, a firewall can be anything that limits access, something as simple as distance, darkness, and cold. If no one can travel there, and if no one can observe it directly, then it works. It serves its function. This firewall idea suggests there might be more beyond the solar system than we're allowed to know, or that the Oort cloud keeps us contained, like a digital fence. It wouldn't have to be perfect, it just has to be far enough and hard enough to reach that we stop trying. Another possibility is that the Oort cloud is a data boundary. In a simulation, you don't need to store everything all at once. You store what's important, and you let the rest load as needed. Like textures in a game, the distant parts of space may not be fully realized until something gets close. The Oort cloud might mark the farthest point where detailed simulation is loaded for our solar system. Beyond that, it could just be placeholder data, nothing fully formed until it's required. That might explain why we haven't detected it directly. A blurry zone, waiting for more input, waiting for someone to make it real by trying to reach it. Until then, it stays quiet. A strange thought follows from this. What if the Oort cloud reacts to us? In some digital systems, the environment updates in response to the user's behavior. If the simulation is efficient, it won't simulate details unless a player or observer goes looking for them. The Oort cloud might work the same way. If we launch probes, it might load in more detail. If we ignore it, it stays in its low-resolution state. If this is happening, we might never know unless we catch it in the act. The real test might come in 100 years or 1,000 when we finally get close enough to look around. If it is part of a larger code, then its purpose might not be to hide anything, but to shape the experience inside. Maybe it slows down incoming threats. Maybe it controls timing. Maybe it's where the system keeps the debris it doesn't want in the main play area. In any case, it might not be random. It might not be just nature. In that sense, the Oort cloud could be one of the most important features in our cosmic neighborhood. These are not easy questions, but standing at the edge of the known solar system, staring into the cold dark where the Oort cloud is supposed to be, they seem worth asking. Interstellar visitors, do Oumuamua and Borisov point to something beyond the Oort cloud? In 2017, something passed through our solar system that didn't seem to belong. It came in fast, didn't slow down, and kept going, never to return. Astronomers named it Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. A year later, in 2019, another object followed, Borisov. But this one looked more like a classic comet, just not from around here. These two visitors weren't part of the Oort cloud. They didn't come from the Kuiper Belt. They were not bound to the sun by gravity. Their speeds and paths told us something clear. They came from interstellar space. That made them the first confirmed objects from another star system to be spotted passing through our own. They offered a rare look at what lies beyond the outermost edge, beyond the frozen reach of the Oort cloud. The fact that we found two interstellar objects in such a short time surprised many scientists. Until Oumuamua, no one had ever seen anything like this. Models had predicted that some interstellar objects might pass through now and then, but they were expected to be extremely rare. Then, two showed up within just a couple of years. Some began to wonder if space beyond the Oort cloud isn't as empty as we thought. Let's go back to Oumuamua. It came in from above the plane of the solar system, moving at around 87 kilometers per second. That speed was too high for the Sun to catch it in orbit. It just curved around the Sun and kept going. What puzzled researchers most was its shape and motion. Observations showed that it was tumbling, spinning in a strange, uneven way. It was also long and thin, like a stretched-out shard. Some models suggested it might be cigar-shaped. Others said it could be flat, like a pancake. Even stranger, it seemed to change speed slightly as it moved away from the Sun. Usually, comets do this when they heat up and release gas, like a jet pushing them forward. But with Oumuamua, there was no visible gas, no tail, no signs of outgassing that telescopes could detect. That led to confusion. Was it made of ice that sublimated in an unusual way? Was it a fragment of some larger object, or was it something else entirely, like a thin piece of material pushed by light pressure similar to a solar sail? This last idea stirred up a lot of debate. Some scientists, including a few well-known ones, wondered aloud whether Oumuamua might be artificial. The suggestion wasn't that aliens had visited, but that this might be debris, like a broken probe or leftover technology, from another civilization. That possibility wasn't widely accepted, but it showed how mysterious the object was. It behaved like nothing we'd ever seen before. Then came Borisov. It was different. Where Oumuamua had been strange and quiet, Borisov looked familiar. It had a comet tail. It followed the same rules as the icy visitors we see from our own Oort Cloud. But it too came in on a hyperbolic path, meaning it wasn't tied to the Sun. It was just passing through, moving at over 30 kilometers per second. Its speed and trajectory told us it came from another star, just like Oumuamua. Because Borisov looked more like a traditional comet, scientists could study it more easily. They found that it had a makeup similar to solar system comets, with some subtle differences. The dust particles in its tail, for example, were smaller and more tightly packed than usual. This suggested it formed in a colder or more compact region of space. It may have been shaped by a different kind of star system, or different conditions in the disk of dust and gas where it formed. Finding these two objects so close together in time made people wonder if these interstellar visitors were more common than we thought. Maybe they pass through all the time, but we just never noticed before. Our tools have only recently become powerful enough to catch them. New sky surveys like Pan-STARRS and the Vera Rubin Observatory are designed to scan wide areas of the sky very quickly. That gives us a better chance of spotting fast, small, dim objects moving in unusual ways. If these interstellar objects are more common, then what does that say about the space beyond the Oort Cloud? These visitors move between stars. They may be kicked out of their own systems by gravitational encounters or stellar events, and then drift for millions or billions of years through the galaxy. That makes space beyond the Oort Cloud seem more alive, more dynamic. It's not just a dark, empty gulf. It could be filled with trillions of rogue objects, tiny planets, shards of rock, frozen comets, drifting between stars. Some may pass close to our system regularly. Others may be flung far out by encounters with stars or planets in other parts of the galaxy. Each one carries a story, a kind of chemical fingerprint of the place it came from. Maybe long-period comets from our own Oort Cloud, and these interstellar visitors aren't so different. If space is crowded with material ejected from other stars, maybe some of the comets we've seen for centuries didn't originate from our solar system at all. Maybe they were captured, drawn in by the Sun's gravity long ago, and made part of our cloud. That would mean the Oort Cloud is a mixing zone, a place where solar system debris and interstellar junk meet. Right now, we can't say for sure. The number of interstellar objects we've studied is still tiny, but each one forces us to think bigger. The Oort Cloud used to feel like the farthest thing. Now it seems like just a thin layer, floating in a much larger sea. Beyond it, objects from across the galaxy may be moving, crossing paths with our solar system in silence. Future telescopes may spot more of these travelers. Future missions may one day even chase them. A fast probe, launched just as one enters the solar system, could try to intercept and study it up close. That would give us a direct look at material from another star, something never touched by the Sun, shaped in a world we've never seen. Are there alien Oort clouds? What other stars might be hiding in their halos? If the Oort cloud formed from leftover material flung outward during the early days of the solar system, then other stars, especially ones like ours, might have gone through the same thing. Then, are there alien Oort clouds out there? The basic logic makes sense. Stars form in clusters from dense clouds of gas and dust. Around each newborn star, a disk of material spins into shape. Over time, parts of that disk grow into planets, moons, and comets. Some objects are pulled inward, others are flung outward by giant planets or nearby stars. If that's true for the Sun, then it's likely true for other stars too, especially those with big planets like Jupiter that can act as gravitational slingshots. In that case, the night sky may be full of stars that are each surrounded by their own halo of icy debris, their own versions of an Oort cloud. But these clouds would be nearly impossible to see directly. If we can't see our own, how could we hope to detect one around another star? Still, some scientists have tried to think it through. One idea is to look for the effects of a cloud, rather than the cloud itself. Imagine a distant star with a strange comet suddenly appearing in its system. If we could watch that star long enough with sharp enough instruments, we might spot the faint trail of the comet passing by. Or we might notice tiny dips in the star's light as the object blocks part of it, similar to how we detect exoplanets. But these events would be rare and unpredictable. We'd need luck and long-term monitoring. Another approach involves infrared telescopes. In theory, if a star's outer region is surrounded by a large number of icy bodies, all absorbing and slowly re-emitting the star's light as heat, the result might be a faint glow. Not a bright one, but perhaps enough to suggest a structure is there. Astronomers have already used this method to find dusty disks around young stars. These disks are warmer and closer in, where planets are still forming. But a few older stars have been found with far colder, more distant disks. These might be something like Kuiper Belts, or even something closer to Oort clouds. One example comes from a star called Vega, one of the brightest in our sky. Infrared observations showed a faint ring of dust and ice stretching far from the star, much farther than the planets we know about. The same goes for stars like Fomalhaut and Beta Pictoris. These systems show signs of structure far out in space, where comets and icy leftovers might still be gathering. While it's not proof of an Oort cloud, it suggests these stars may have something like it. There's also the idea of watching comets directly. If another star is surrounded by a halo of icy objects, some of them might fall inward, just like in our system. As they heat up, they release gas and dust, forming tails. If those comets pass between us and the star, we might catch a faint change in the light. Astronomers call this spectral dimming, and it's one possible way to detect exocomets. In fact, a few exocomets have already been spotted. The star Beta Pictoris again stands out. It's been watched for years, and scientists have seen sudden brief dips in its light that don't match planets. Instead, they seem to come from small, dusty objects on fast, unpredictable orbits. These may be exocomets falling in from that star's distant reservoir of debris. If that's true, then we may already be seeing the edges of another star's Oort cloud in action. But the signals are weak, and the details are hard to confirm. We can't track the full path of an exocomet the way we can with one in our own system. We don't know exactly where it came from or where it's going. All we have is a short-lived signal and a lot of possibilities. Still, the hunt continues. If we could confirm the presence of an Oort cloud around another star, it would tell us a lot. It would suggest that these halo-like structures are a natural part of stellar evolution, that the outer regions of space are not empty, but full of quiet, drifting material. It would also help us understand our own solar system better. If we could compare different clouds, how big they are, how dense, how icy, it might tell us how unique or typical our own cloud really is. It could also help answer questions like how many comets are likely to strike planets over time, or whether other stars have similar comet-driven events, Maybe even mass extinctions like those suspected on Earth. If alien Oort clouds are real, then cometary impacts might be a universal feature of planetary life, something that happens everywhere, across time. Every now and then, a star passes close to another star. If a passing star moves through the outer edges of another star's Oort cloud, it might disturb some of the icy objects. A small burst of comets might fall inward toward the star. If we were watching at just the right time, with a sensitive enough telescope, we might see a spike in comet activity. It would be rare, but it could serve as proof. There's one more idea still on the edge of what we can test. Some scientists wonder if we could someday detect rogue comets, not from our own cloud, or even from another star, but from one that was flung out of an alien Oort cloud long ago. These would be true interstellar comets, but with different chemical fingerprints. If we could catch one passing by and study its contents, we might know it was formed around another star, then ejected into deep space, only to arrive millions of years later in our neighborhood. To do this, we'd need fast-moving probes or incredibly sensitive telescopes. But even if we only see the chemical traces, signs of different water ratios or rare compounds not found in solar system objects, it might be enough to suggest an origin far beyond our system. The idea that the night sky is filled with stars, each surrounded by its own cold halo of drifting debris, makes the galaxy feel richer, older, and more connected. Somewhere out there, frozen relics may be circling distant suns, trapped in silent orbits, untouched since their birth. They might be the most common leftovers in the universe, forming quiet borders around stars that shine from billions of miles away. Could life hide in the Oort cloud, rogue microorganisms in ice and rock? It's easy to think of the Oort cloud as just a frozen shell, too far for anything interesting to happen. No sunlight, no heat, no atmosphere. Just trillions of chunks of ice and rock moving slowly around the sun, barely stirred since the early days of the solar system. But what if, hidden inside one of those quiet objects, there was something else, something alive? Life is stubborn. On Earth, it shows up in places we never expected. Tiny microbes live deep under the ocean floor, cut off from sunlight for millions of years. Some survive inside Antarctic ice, sealed away since before the pyramids were built. There are even bacteria found in old salt crystals that may have been dormant for tens of thousands of years and still revived when conditions were right. If life is possible in these cold, dark places, then maybe it could also survive out near the edge of the solar system. One idea is that simple life might have formed on the early Earth, or even before Earth, and then spread out through the solar system by accident. It's called panspermia. A large asteroid hitting a planet could blast material into space. If any of that material had life in it, it might travel for thousands or millions of years. Some of it might crash into other planets. Some might escape entirely. And some could end up in the outer solar system, caught in slow looping orbits around the sun. Now imagine a rock just a few meters wide, containing a few hardy microbes buried deep inside. If it gets pushed far enough out, it could end up frozen solid in the Oort cloud. It would stay cold, shielded by thick ice. Radiation from space would be a danger, but not all parts of an object are equally exposed. Inside a thick enough shell, deep down where the cosmic rays can't reach, the core could remain protected. That protection might last for billions of years. No one has found a living organism in space, but life's ability to survive extreme conditions keeps raising eyebrows. Scientists have taken bacteria to the International Space Station. Some survived long exposure to vacuum, radiation, and freezing temperatures. In one case, microbes on the outside of the station were still alive after more than a year. Other studies show that spores, the hardened survival form of some bacteria, can last for centuries if they're kept dry and cold. Inside a solid Oort cloud object, conditions might be just right to allow for long-term survival. Maybe life didn't just end up in the Oort cloud by accident. Maybe it started there, or somewhere like it. Early in the solar system's life, when the planets were still forming, there were regions where organic chemistry was taking place. Complex molecules were forming on icy grains and inside comets. These same kinds of molecules have been found in meteorites and comets that hit Earth. Some scientists believe that the building blocks of life could have come from these frozen bodies. If the right chemistry was happening inside them, maybe under the influence of mild heat or pressure from radioactive decay, it's not impossible that something more developed could emerge. Life needs liquid water to form. That's a problem in the Oort Cloud. Temperatures are far below freezing, and the sun is just a dim dot in the sky. But in the cores of some objects, especially larger ones, internal heat might be enough to keep a small pocket of water from freezing. Not warm oceans, like on Europa or Enceladus. Just a small chamber, maybe no bigger than a room, sealed inside an icy shell. The source of that heat could be radioactive isotopes, like those found in meteorites. As they decay, they release energy. On Earth, this helps keep the core hot. In a much smaller body, the heat would be faint, but if well insulated, it might be just enough. Eventually the heat would fade and the pocket would freeze. But for a short window of time, thousands or maybe even millions of years, it might be enough to let chemical reactions happen, maybe even enough for something alive to form. Then comes the long sleep. The water freezes, the heat dies out. Whatever existed inside becomes trapped and preserved. If such life exists, or once existed, it would be incredibly hard to detect. Oort Cloud comets might be suitable messengers. As they fall into the inner solar system, their ice turns to gas. That gas carries dust and molecules into space. By studying the makeup of these comets, scientists have found organics, carbon-based compounds, some similar to those found in living things. These are not proof of life, but they do show that complex chemistry exists in these frozen places. One day, if we send a mission to sample a comet from the Oort Cloud, or one recently dislodged from it, we might find something more. Maybe not a living microbe, but a structure. Something that doesn't look like it came from random chemistry. Even a single unusual molecule could raise big questions. There are people who wonder if life might not only survive in the Oort Cloud, but thrive in ways we can't imagine. Maybe it exists in forms that don't need heat or water. Maybe it uses chemistry we haven't yet discovered. In that case, the outer solar system could be full of hidden life, waiting silently in the dark, never touched by sunlight, never known to us. Even if that idea is far-fetched, the Oort Cloud still matters in the search for life. It may be a freezer full of ancient material, unchanged since the dawn of the sun. Studying it could help us understand where Earth's water came from, or where its first organics arrived from. It might even tell us whether the chemistry of life is something rare, or something that naturally happens wherever ice and time meet. As of now, it's all speculation. But it's not wild speculation. Every time we study life's limits, those limits move. The discovery of extremophiles, organisms that live in boiling vents, acidic lakes, and frozen tundras, has made it harder to say what's impossible. And in that silence beyond Pluto, there may be things we've never thought to look for. If life does exist in the Oort Cloud, it would be a quiet life. No big creatures, no ecosystems. Just a few hardy cells, waiting for warmth that may never come. Or maybe, once every few million years, a passing star nudges one of these objects inward. It falls toward the sun. It begins to warm. The ice cracks. The gases hiss out. And maybe, just maybe, something stirs inside. Could the Oort Cloud hide the remains of other civilizations? The Fermi paradox begins with a simple idea. In a universe this large, with so many stars and planets, intelligent life should be common. So where is everyone? Why haven't we seen signs of aliens? Some say the answer lies in the Great Filter, a barrier that stops life from becoming advanced and spreading across space. The filter might be behind us, meaning life is rare and precious. Or it might be ahead of us, meaning most civilizations don't make it very far. Either way, we're left wondering if something, somewhere, wipes out intelligent life before it can leave a mark. If that's true, then where would we find the leftovers? If a civilization rose and fell long before Earth had cities, or even life, it might have sent probes into space. Maybe it built machines that traveled between stars, or left warning signals in deep space. Over time, most of those artifacts would decay, crash into stars, or drift into the void. But a few might survive, and if they did, they'd need a quiet place to hide, somewhere dark, cold, and stable. The Oort Cloud, in that sense, is the perfect graveyard. Unlike the inner solar system, the Oort Cloud doesn't change much. Its objects move slowly. There's no heat, no strong radiation, no atmosphere to wear things down. If you wanted to hide something for 1 billion years, an old probe, a listening post, or a digital archive, this would be the place. It's far enough out that nobody would notice it, but still orbiting the Sun. From there, a small device could watch everything happening in the solar system, like an old security camera in a forgotten hallway. The idea of alien artifacts in the Oort Cloud may sound far-fetched, but even mainstream scientists have brought up the idea of interstellar archaeology. If intelligent life once existed in our galaxy, traces of it could still be out there. Not signals, but hardware. Long-dead machines, old probes, outposts made of metal and plastic, drifting silently between stars or trapped in the gravity of another solar system. They might be completely powered down, but their structure, shapes, patterns, or even the materials used would set them apart from natural objects. Not every Oort Cloud object would be alien, of course, but 1 out of 1 trillion could be different. Not by being shiny or artificial in shape, but by showing signs of design. Maybe sharp angles, or metal elements that don't match solar system chemistry, maybe magnetic patterns that seem too precise. It wouldn't take much to make scientists pause. This also ties back to another idea, von Neumann probes. These are self-replicating machines that could, in theory, spread through a galaxy over millions of years. They'd land on asteroids or moons, mine materials, and build copies of themselves. They wouldn't need to travel fast, just steady and patient. Over enough time, even a small number of them could reach every star. If such machines were ever built, some might have made it here. And where would they park? Not in Earth orbit, where we'd notice. Not on Mars, where solar wind and dust would slowly destroy them, but deep in the Oort Cloud, where nothing changes for eons. Another version of the theory is that alien civilizations, after reaching a high level of technology, might choose to disappear, not by dying out, but by hiding. Some call this the zoo hypothesis, where advanced life watches us from afar, waiting for us to mature. If true, their monitoring posts might not be nearby, but tucked into the dark outer reaches. Every time a long-period comet appears in our skies, it's likely coming from the Oort Cloud. Most of them behave like natural bodies, but a few don't. Some have strange orbits or unusual speed. Others seem too active or too quiet. Occasionally, a comet is first thought to be artificial because of its odd movement, only to be later explained by natural forces. But what if one isn't natural? What if it's a shell covering something else? Something ancient and silent that's been waiting for the right moment to wake up. We don't yet have the tools to check. We can track comets, but we don't get close enough to study them in detail unless a mission is launched. So far, only a handful of comets have been visited by spacecraft, and none from the Oort Cloud. That leaves open the question of what we're missing. Could an alien relic pass through the solar system and leave before we ever notice? Even our current deep space missions may one day drift into the Oort Cloud. They will stay there for a long time, possibly forever. To an alien astronomer visiting our system in the distant future, these spacecraft might seem strange. A tiny metal object among icy bodies. From their perspective, we may have already placed our own artifact into the dark. There's also the idea that the Oort Cloud might not just contain old alien machines, but wreckage. If the Great Filter is real and civilizations destroy themselves in some final act, the aftermath might scatter across nearby systems. bits of debris, machines no longer working, frozen, shattered satellites thrown into interstellar space. Some of that material might be caught in solar systems like ours, slowly drifting into outer orbits. Again, the Oort Cloud becomes the last stop, a place where the galaxy's forgotten stories might come to rest. Of course, all of this is speculation. There's no direct evidence of alien technology in the Oort Cloud or anywhere else. But the silence itself is what makes the Fermi paradox so haunting. If we're truly alone, then the Oort Cloud is just ice and rock. But if we're not, and other civilizations once explored the stars, then some part of them might still be here, buried in the cold. It would only take one discovery to change everything. A shaped fragment, an unnatural signal echoing from the outer dark. That's the allure of the Oort Cloud. It's a blind spot, and until we explore it, we can't rule out what might be waiting there. Shadows in motion. Could hidden dark matter lie in our Oort Cloud? Some have wondered if the Oort Cloud holds more than just comets and icy debris. Maybe it also hides something much stranger, something we've been chasing for decades, yet never seen directly. Maybe, in its quiet emptiness, the Oort Cloud is shaped not only by gravity from the Sun or nearby stars, but by something darker, something known as dark matter. Dark matter is one of the biggest mysteries in modern science. It's not just a theory, there's overwhelming evidence that it exists. Galaxies spin faster than they should, galaxy clusters hold together more tightly than expected, and light bends around space in ways that don't make sense if we count only the visible matter. Scientists believe that most of the mass in the universe is made up of this invisible material. It doesn't emit light, it doesn't absorb it, and we can't touch it. But it has gravity and it shapes the structure of the cosmos. We know dark matter must be out there, but we don't know what it is made of, and we don't know exactly where it is. Most scientists believe it's spread throughout the universe in giant halos, stretching across galaxies, and possibly filling the spaces between stars and planets. If that's true, then some of it might be here too, right in our own solar system. Could some of this dark matter be hiding in or around the Oort Cloud? And if it is, how would we tell? Unlike comets or rocks, dark matter wouldn't shine or reflect sunlight. It would be like a ghost in the data, pulling and pushing things, but never showing itself. If a cloud of dark matter drifts through space, it could pass through planets, stars, or comets without being seen. Yet its gravity would leave fingerprints. It might tug on objects in subtle ways, changing their orbits or their speeds. It might even stir up the Oort Cloud, knocking a few icy bodies loose and sending them plunging toward the inner solar system. Some researchers have suggested that dark matter might actually help shape the Oort Cloud itself. When the solar system was young, many rocks and comets were tossed outward by the gas giants. Most of these icy leftovers either fell into the sun or escaped into deep space. But some were caught at the far edge of the sun's gravity. If dark matter was also present in that region, its gravity could have helped trap more material. It could have thickened the outer shell, adding an invisible mass that helped shape the whole structure. Others have gone further. They ask whether clumps of dark matter might exist inside the Oort Cloud itself. Maybe dark matter isn't evenly spread out like a mist. Maybe it clumps into dense blobs, almost like invisible planets or clouds, that drift through space. If one of these dark matter clumps passed near our solar system, it might have left a mark. It could have pushed on the Oort Cloud, stirred its objects, or changed the flow of comets. Some even wonder if strange patterns in comet appearances, clusters or sudden spikes, might be caused by something hidden like this. There's no direct evidence for this yet, but some models predict that the solar system might have passed through dense filaments of dark matter in the past. These structures, shaped by the early universe, may stretch across space like cosmic threads. When the solar system drifts through one, it might create waves of gravitational influence. That influence could jostle the outer solar system, nudging the Oort Cloud like a hand brushing the edge of a spider web. The big challenge is that dark matter doesn't interact with normal matter in ways we can easily detect. it only acts through gravity, so any search for it in the Oort Cloud has to rely on indirect clues. Scientists look for small shifts in the orbits of comets. They track how long-period comets behave over time, how fast they move, how their paths curve, and whether their patterns match what we expect from a cloud made of just ice and rock. If there's an invisible mass shaping them, that could be a hint. Some astronomers have even proposed sending future spacecraft deep into the solar system to measure gravity very precisely. If a probe moves slightly off course, or if it speeds up or slows down without an obvious reason, that might suggest it's passing through a patch of dark matter. The effect would be tiny, but with enough accuracy and enough data, we might see something strange. Others think we might find clues in the timing of comet impacts. If comet strikes on Earth follow a loose cycle repeating every 25 to 30 million years, then this cycle could be caused by the solar system moving through bands of dark matter, triggering waves of comet activity. It's the kind of pattern that could point to something hidden. Another theory suggests that dark matter might not be entirely passive. Some forms of dark matter might interact weakly with normal matter, just enough to leave a signal in the form of heat or faint radiation. If that's true, then objects in the Oort Cloud might hold a tiny amount of that signal. Maybe the ice out there is slightly warmer than expected. Maybe the rocks glow faintly in a strange spectrum. If we could get a spacecraft close enough, we might find clues written in the molecules themselves. Some have stated that dark matter might collect inside large objects, like stars or even planets. If it sinks to the center, it might affect how those objects behave over billions of years. Perhaps the Sun might contain a tiny dark matter core, built up slowly over time. If that's true, then maybe the Oort Cloud feels that extra pull. Maybe the whole cloud is shaped slightly differently than we think. The Oort Cloud, being so distant and so hard to observe, remains the perfect hiding place for ideas like this. In the coming decades, better telescopes might let us map the edges of the Oort Cloud more clearly. Future probes might fly into its outskirts and send back readings. If there's dark matter drifting there or shaping the cloud's form, we may someday notice. For now, the shadows remain in motion, silent and full of questions. Gravitational noise at the edge. Can ripples from the galaxy disturb the cloud? Out at the solar system's edge, the Oort Cloud sits in quiet stillness. But even here, in what seems like total calm, there may be forces moving beneath the surface. Subtle, slow and wide across time, the galaxy itself may be sending signals, gravitational ripples, that pass through the cloud. The Oort Cloud, for all its distance, is not immune to what happens in the Milky Way. One of the biggest influences comes from something called galactic tides. Just as the Moon pulls on Earth, the Milky Way pulls on everything inside it. The stars, the gas, the dust, and even the Oort Cloud are affected by this constant pull. The solar system is not floating in isolation. It moves through the galaxy, orbiting the galactic center once every 225 million years or so. As it does, the gravity of the Milky Way itself bends and stretches space, and this force can reach even the farthest parts of the Sun's domain. The outer halo of the Oort Cloud is held only loosely by the Sun. Its objects are fragile in their orbits, balanced on the edge of being lost to space. The tidal force from the galaxy, though extremely weak at any single moment, can nudge these bodies gently over time. It might be enough to change their orbit slightly, tipping them inward toward the planets or outward into interstellar space. Galactic tides don't act all at once. They move like a slow wind, pushing with patience instead of speed. But if the solar system passes through certain parts of the galaxy, such as dense regions or spiral arms, the tidal effects might become stronger. This is especially true if there are nearby stars or clusters with large gravitational influence. Beyond tides, another possible source of disruption would be dark matter clumps. If the solar system ever passes near one of these clumps, or if one moves through the region of the Oort Cloud, it might stir things up. The gravity from the dark matter could pull on the comets, changing their paths. Another disturbance could come from gravitational waves. These are ripples in the fabric of space-time, predicted by Einstein's theory of general relativity. They are caused by very large events, like black holes merging or neutron stars colliding. Gravitational waves stretch and squeeze space itself as they move through the universe. In 2015, scientists finally detected them directly using ultra-sensitive equipment on Earth. These waves were tiny, smaller than an atom in size, but they proved that space could indeed ripple like a sheet of fabric. Normally, gravitational waves are far too weak to affect something like the Oort Cloud. The waves detected so far pass through us without any noticeable effect. But if a very large wave passed nearby, perhaps from a massive black hole collision closer than usual, it might leave a faint mark. Perhaps it could pass through the Oort Cloud and gently alter the orbits of its objects. The effect would be small and hard to detect. But it's possible that these waves occasionally shake the far edge of our solar system. Then there's the galactic environment itself, which is not fixed or empty. The Milky Way contains streams of stars, loose clouds of gas, and even ancient remnants from long-gone satellite galaxies. As the Sun moves through the galaxy, it might pass near one of these features. In fact, scientists have already found that the solar system sometimes moves through the galactic plane, the flat part of the galaxy where stars and dust are more concentrated. When this happens, it might cause extra pressure on the Oort Cloud. A thick cloud of dust or gas might add extra drag, or its gravity might pull on the Oort Cloud just enough to trigger changes. Some models suggest that this kind of event might be responsible for waves of comet impacts on Earth. If something shakes the Oort Cloud hard enough, it could send a rain of comets inward. Over time, that could lead to impacts on planets, including Earth. Even passing stars can have an effect. One such star, known as Gliese 710, is expected to pass relatively near the solar system in about 1.3 million years. It may pass close enough to send comets from the Oort Cloud raining toward the Sun. There is also a background hum of motion through the galaxy. The Sun moves, the stars move, the galaxy itself has structure and movement. The Oort Cloud, floating far from the center of the solar system, is caught in this slow dance. It drifts with us, pulled by the Milky Way's tides and stretched by invisible fingers. Every comet, every slow orbit is part of this broader galactic motion. If we could watch the Oort Cloud in real time over millions of years, we might see these effects as slow waves, clouds stirring, comets nudged, patterns shifted. We might see ripples coming from the galaxy itself, like distant thunder shaking the edge of a quiet pond. We might begin to understand how the structure of space around us is not still, but always in motion, shaped by forces we barely notice. Today, we don't have the tools to see these changes directly. We catch comets only when they finally swing into view. We can't yet measure tiny shifts in orbit from far away, but as long-term data grows, we may start to detect the faint fingerprints of these galactic whispers, whether from tides, dark matter, waves, or passing stars. The Oort Cloud may be more alive than it seems. Not in the sense of life, but in motion, a slow, long echo of the galaxy's own heartbeat. If the Oort Cloud collapsed, the consequences of a comet storm. Armageddon. If the Oort Cloud were to collapse, or even just partially shift, there would be consequences that could stretch across the entire solar system. Though the cloud seems distant and harmless, it holds the power to shape life on Earth in dramatic ways. For most of human history, we've only seen bits and pieces of it, comets that appear suddenly in the sky and vanish again. But those short visits may be just a glimpse of a much larger, quieter presence. The Oort Cloud could be one of the biggest threats we don't think about. A collapse doesn't mean the entire cloud suddenly falling apart. It wouldn't be an explosion or a flash of light. It would be slower, but no less dangerous. The cloud is made up of countless icy bodies that have stayed in place for billions of years. But if the balance holding them in place shifted, they could begin to move. and if enough of them began falling inward toward the planets, the effects could be massive. The most likely result of such a shift would be a comet storm. One or two comets arriving from the Oort Cloud isn't unusual. We see that all the time. But if hundreds or even thousands of objects began to make their way into the inner solar system over a short period, the situation would change quickly. These objects move fast, sometimes tens of kilometers per second, and they carry enormous energy. When one hits a planet, the impact is like a bomb, far stronger than most nuclear weapons. Earth has been hit before. The scars of these impacts are scattered across its surface. Craters, layers of shocked rock, and even possible extinction events tell the story. Most scientists believe that at least one of Earth's mass extinctions was caused by a comet or asteroid impact. The event that wiped out the dinosaurs may have come from the sky, though it's not clear if it was a comet or an asteroid. In a comet storm from the Oort Cloud, we wouldn't be dealing with a single impact. There could be waves of them. Some would miss the Earth, some would burn up in the atmosphere, but others might hit. The problem is not just the individual impacts, it's the rate. Even one large comet can be devastating. Several in a row could destroy entire regions. If the impacts kept coming for decades or centuries, Earth's climate could shift. The sky could fill with dust. Crops might fail. A chain reaction of disasters could unfold. The trigger for such a collapse could be many things. Many have already been discussed, but another cause could come from within the solar system itself. A massive change in the orbit of a planet, if that planet were somehow disturbed or thrown off course, might send ripples outward that eventually reached the Oort Cloud. It's not clear how strong such a signal would have to be, or if it could actually cause a collapse, but it shows how interconnected the system is. Even small shifts, given enough time and distance, might have large effects. Once the comets began their inward journey, there would be little we could do to stop them. At first, they would be invisible, just faint, frozen rocks drifting toward the sun. Only when they got closer would we begin to detect them. The best telescopes might spot them months or even years in advance, but that may not be enough. These objects often arrive from high angles, moving in strange orbits. They don't follow the paths of the planets, so they're harder to track. A swarm of them would overwhelm our ability to monitor and respond. Efforts to defend Earth from impacts are still in the early stages. A few space agencies are working on deflection technologies, methods to push an asteroid or comet off course. But these plans usually rely on years of warning and precise tracking. In a real storm, we might not have that luxury. There could be too many targets coming too quickly. Some might be missed until it's too late. If even one large comet hit the ocean, it would send shockwaves across the sea. Massive tsunamis could flood coastal cities. If it hit land, the explosion could flatten forests, destroy cities, and start wildfires. The dust would rise into the air and block sunlight, cooling the Earth. A nuclear winter scenario could begin, not from war, but from a natural disaster no one could stop. If multiple impacts happened within a few years, the effects would grow. Agriculture might collapse, animal species would vanish, disease and famine could spread. Civilization might survive, but it would be changed. The idea of a comet storm is not just an abstract risk. It's a real possibility, even if the odds are low. The Oort Cloud is so far away that it's easy to forget. But that distance can be deceptive. In space, time and distance can collapse quickly when the right conditions appear. A change that begins 50,000 AU from the Sun might take thousands of years to arrive, or it might take less. Some long-period comets arrive with little warning, taking only a few months to pass from the outer solar system to the inner. If there were hundreds of them, we might not have enough time to react. The comets wouldn't just pass Earth, they'd cross the orbits of all the planets. Impacts could happen anywhere. Mars might be hit. Jupiter's strong gravity might pull in some, possibly saving the inner planets from the worst. But its own moons might be at risk. The asteroid belt could be disturbed. The whole system might fall into a period of chaos. Over time, things might settle down. The remaining comets would either fall into the Sun, be captured by planets, or fly off into space. But the damage would be done. Earth would carry the scars, both physical and biological. The sky would have changed. The patterns of life would shift. This scenario is extreme, but not impossible. It's one of those quiet dangers, too distant to cause panic, too large to fully understand. It's hidden behind the curtain of deep space, in a region we can't control. The Oort Cloud may be silent now, but it holds the potential for loud, dramatic events. We don't know if the Oort Cloud has collapsed before. There may be signs in the ancient records of the Earth, or it may still be waiting. A future moment when the balance breaks and the sky begins to fall, one comet at a time. And on that humbling note, this voyage comes to a close. What would you like for us to cover next? Sound off in the comments below, and if you enjoyed the video, consider leaving a like and subscribing. Thanks for watching.